you go to the e-learning on UTM's website, you can see this MKEL1183 section 05, and you can see there's a course information here. And we also have the timetable. Okay, so based on this timetable, we're going to set a test exam. Now, our meeting link is always this one, so that's easy to remember. And at the same time, you can also click this link, which is the Google Sheet here. All right, and this Google Sheet is open to everyone. Okay, and what I need you to do later is that I'm going to have a group assignment as well, and one group should have at least 4%. Okay, and one group will have 5 because we have 29 students. So you can just click here, and it will bring you to this Google Sheet, and based on your preference, you can say I want to be with this person and this person and this person and this person. For example, really up to you, and you can have 4 people in a group. Okay. Now, otherwise, I will just put 1, 2, 3, 4, and so on. Okay, so at this moment, I'll just give you a flexibility to just choose whoever you want to be in your group. Okay, let me just fix this. Okay, the next thing is this WhatsApp group link, and I can see that some people have started to join the WhatsApp group already, so that's good. Okay, so maybe up-to-date information or urgent information I will dispatch to WhatsApp. Down here you can see the lecture class notes, but it's not really in order. I mean, I just put all of them here, but this is lecture 1, lecture 2, and lecture 4, lecture 3. So everything is there, but probably not in the correct order. Okay, so just have a look here. And this is our primary reference book. I'm not supposed to give you this PDF book. It's considered illegal, I guess. But I guess if you search on the internet, you're still going to find it anyway. So I'm just going to put this primary reference here. And there are some test papers, test 1 and test 2 from previous semester. You can see here as well. And also 2 sets of final examination papers here. And more things will appear here later as more contents, as I have more contents to share with you. Okay, so but at this moment, you can just have a look at these things already. All right, so now let's have a quick look at our timetable. So that we can, have a look at when we can do the test and so on. So we are right now in week number 5. Okay, so it's actually the end of week number 5, and you're having a class with me today. And the following class will be on week, where is it? I see. Okay, at week number 11. Okay, at week number 11, we're going to have our second class, and our final class will be on week number 14. That's going to be our final class here. So I have a few students who are not able to attend this week 11 due to company training. So I'm wondering if you are taking this. Are you taking any classes in this advanced microprocessor and advanced digital system design? Are you taking any of this? Yes, no?
Yep. Advanced microprocessor system.
All right, okay, no problem. Okay, so actually I just want to have a date for our test 1. So is it okay if I make the test on week number 7 or week number 8? Week number 8 Saturday for 1 hour only? So test number 1 will consist of the material that we learned today and tomorrow. Okay, so I'm planning to have test number 1 on the 14th of May, Saturday for 1 hour at your preference at 9 a.m. in the morning or so. Okay, is that okay?
Yeah.
Yes, okay. Shafiq says okay, I think. Yes. All right. If there's an objection, you can just turn on your mic or just put it in the chat. Otherwise, I will consider it as a unanimous okay. Okay. So our what we call provisional test 1 will be on the 14th of May, Saturday for 1 hour. Okay. And you can tell me what time you like. Okay. Since it's just 1 hour. Yes. Yes, Shakir has raised a hand. Anything? I guess it's okay, right? Okay, 1 hour in the morning or 1 in the afternoon or 1 hour at night, really up to you. Okay, if you need the time to revise, if you want it indeed at night, then fine, I can make it at night. Okay, it's just 1 hour for test 1. Okay, and yeah, so that's our class timetable, and our final examination timetable is also available online, and you can check that as well. Okay. All right, so that's about our class arrangement. So let's put it here. Test one is, let me put there, is slated for 14th of May 2022. 1 hour, can discuss time. Okay. I can make it at night. I mean, maybe you get off from work on Friday and you want to study the morning and afternoon of Saturday, and you are more comfortable to take it at night. Then we can put it 1 hour at night. Okay, I think 1 hour at night would be better, right? So provisionally at night. All right, so we got that out of the way already. Okay, and the next thing is that let's go and have a look at the course information. So I got it open here already. So the first thing is that this course covers the hardware structure of a modern programmable computer, which we are going to cover in this class, obviously, including the basic laws underlying the performance evaluation. And you will learn about the control and data part of the RISC CPU. So we're using a RISC CPU. Particularly is the RISC-V, and how to make machine instructions execute simultaneously through pipelining and also parallel processing, and also how to design a fast memory system. Okay, so that's going to be the basic synopsis of this course, and my office is here, my contact number is here, my email is here. You can just have a look there. And the three course learning outcomes are the first one is to understand the fundamentals of quantitative design and analysis of processor architectures, and that's going to be covered in test one and also final examination. And then we have the in-depth study of different process architectures and impact of parallelism. That will be on test two and also final and also homework. And review of future paradigm, that will be entirely on homework. Okay. So I guess you're more interested to see what are the contents and also the assessment. I think that's most important. Okay. The first one is that today and in the next 4 days, if you look here, we basically have 11 chapters. So 11 divided by 3 weeks. I'm going to cover 4 chapters per week. Basically 2 chapters per day, one in the morning and one in the afternoon. And so today, over this weekend, we're going to cover lecture 1 to 4. In the next weekend, we're going to cover 5 to 8, and in the final weekend, we're going to cover 9 to 11 only. Actually, as you go more to the end, it's more theoretical and it's faster to cover. Basically, only theories only. Okay. So today, in the first 3 weeks, we're going to cover about in the first 4 weeks. Okay. Basically. 4 chapters. Okay, so the basics of quantitative analysis and computer architecture, the ISA, the data part, the pipelining, and the next meeting will be memory hierarchy and optimization, data parallelism. Okay, and at the end we're going to look at this multi-core architecture. Okay, so that's going to be our uh, contents. So basically you can just look at the notes. All the notes are there. Those are the things that we are going to cover. All right, maybe I can create here. Let me just stop sharing for 1 second here, and let me try to do something. So let me just put here. Okay, let me. Okay, just give me 1 second. Okay, let me. I want to get some info from you. Okay. Let me give me. Sorry. Okay, so I've actually opened a poll in WebEx. Okay, you can just look at the poll bar there. I'm asking you 3 questions to get just some general idea from you. Okay, the questions are: how many of you have taken some sort of a computer architecture class during your undergraduate? And how many of you have taken what we call a microprocessor? I believe you have. Okay, and how many of you are well versed in C programming? So when I say microprocessor, means you know about assembly language and so on. So just a quick, you can say no if you have not taken, because I want to know that what kind of level are you at. Okay, so you have 5 minutes to answer these 3 questions. Please do so. So at least I know and I can gauge your basic understanding before we begin this class. Okay. All right. So while the poll is running, so let me just continue my explanation again. Okay, so we're going to have the following assessment. Okay, and there's a bit of change here. Test 1 is 15%, test 2 is 15%, and then we have an individual assignment. Okay, so the individual assignment would be, I think it's 5% or 10%. Okay, so it's going to be where you're going to write a short paper. Okay, based on some literature reading. There's going to be one individual assignment and also one group assignment, and I'm going to explain about these 2 things tomorrow. Okay, tomorrow the 4th chapter is a bit short, so we'll have more time to discuss about the assessment tomorrow. So that's going to be our assessment. Okay. Okay, so we're going to have test 1 on the 14th of May, and we're going to have test 2 in our last meeting. Okay, so one test on the 14th, another one in our last meeting, and 2 assignments in between, one individual and one group assignment. Okay, and that is where the group assignment comes. So please select your grouping here. Okay, so if you don't have this link, let me just put this. It's on e-learning, the link. Okay, or I can just put it in the WebEx chat. Okay, and you can click there and right away come here and just put your group number. Okay, anybody who starts can put the group number here and so on. Okay, if you need some time to decide, no problem, but just fill it up here so I can track the groups. Okay, now I guess you have heard that one of our meetings will be physical. So the plan is that our 3rd meeting will be conducted physically in Penang. Okay, so the details of the place uh, will be will be told to you later lah, okay, since the place has not been arranged yet. Nevertheless, for those who are unable to attend due to being in a different location, you will be allowed to attend through online. Okay, so we're going to have a hybrid class there, physical and also online. Okay. Okay, so the primary reference book is the Quantitative Approach 6th edition, Computer Architecture Quantitative Approach 6th edition by Hennessy Patterson. So let me just show you the book. Just 1 second. Okay, so this is the book. Okay, and okay, this is the book, and I've already put the book on e-learning, so you can have a read about on this book as well. So I mean, if you don't understand some material, you want to look at more examples, you want to do some exercises, there's a lot in this book. Okay, so do have a look here, for example, explaining what is data hazard and so on. So you can read about these things in the book in your free time. Basically, you must read, okay, to increase your knowledge. Okay. Okay, all right. That's all. That's all for our explanation about the CI. Okay, and let's have a look at the poll. Another 1 minute remaining with one person who has not answered yet. Okay, perhaps he's on mobile. Okay, but it's in progress. So let me just wait for that to complete. Okay, so I know at least some understanding about your background. So it says that computer architecture 10 have never taken before. Microprocessor, almost everyone. C programming, some of you, more than half, have not taken this. Okay, all right. So nevertheless, which means you have to do a bit more, reading. Okay, since these are the 3 things that we are going to use in our class: a bit knowledge on computer architecture from undergraduate, a bit of microprocessor, and a bit of C programming, but not a very deep C programming. It's just simple C programming to illustrate what happens on the CPU. Okay. All right. Okay, so the poll has ended, and let me just look at the poll results. Okay, so basically 50% or some sort of around 40% have not taken any what we call any computer architecture class before. Okay, never mind. I'll try to cover as much as possible in class so that the learning is okay, so we are able to have a good learning outcome, right? Okay, so let's begin today's class. So I'm going to begin with chapter number 1. If you have any questions, you can just ask. Maybe I should make another poll here. Let me just, for the fun of it. Let me ask you a few questions. Okay, so you can just fill up this short poll, last poll for today. Okay, so just want to get a few feedback from you, whether you prefer online, physical, or will you be able to attend the third meeting physically? And if not, or if yes, whatever, where are you currently stationed in Malaysia? Okay, are you in Penang or Perak or Sabah or Kuantan? I do not know. So that's what I want to find out. Okay. Okay, so the sooner this finishes, so I can begin the class. Okay. Okay, so Still filling up the poll. Still 2 minutes remaining. Okay, so I think we should begin by 9:30. All right. Consider this as a break. Okay, just 1 second. Okay, taking very long to fill up the poll. Okay, never mind. Okay, okay, just 1 minute remaining. So I think I should get the complete results in a few seconds. This is one last person filling up the poll. Okay, so for those who have not scanned yet, you can take the final moment here to scan. Okay, I only give you this QR code once a day, so it's considered attendance for the whole day. So if you have not scanned yet, the final 1 minute to scan this. Okay. 28 including me, so that's about right. Okay, stop that. Okay, so 90% of you prefer online class. Okay, 4 did not answer. Can you attend the third meeting physically? 30% says yes. Currently, I'm stationed in Penang, Selangor, Kuching, Pahang, Perak, hometown India. Oh, this one in India. Okay. Malacca, Temolo, Pahang, and if you have 10 minutes visiting, if you don't have time to prepare, as mid-sem will be 6 weeks direct of classes. No, you can just attend the class online. Okay. Okay, never mind. Okay, so I got this data and I can just have a look at this data later. Okay. Okay, thank you very much for the feedback. Okay, so it's time to us time for us to begin our today's class. Okay, great. Okay, so so again, Assalamualaikum and a very good morning. So today, this morning, I'm going to cover lecture number 1, which is understanding computer architecture. Okay, all right. So these slides are actually from these two books. One is the Patterson and Hennessy 2017 chapter 1 and Hennessy and Patterson 2017 chapter 1. So basically, these two people they write two different books. Okay, so the Patterson Hennessy means Patterson's name comes first, followed by Hennessy. So that's one computer architecture book. The other book is actually computer architecture and organization. So so this coming from these two books lah. Okay, it's not that why I wrote Patterson Hennessy and Hennessy and Patterson, because there are two books and depending on who is the first author. Okay, okay, so The reason for why we have such a good computer revolution today is underpinned by this Moore's law. I think you know what Moore's law is about. So Moore's law actually says that the number of transistors actually double every 18 months. Okay, so I think to some extent it's still sort of alive, at least in the GPU and also Apple's M1 chips. Okay, so it proves that the Moore's law is still sort of alive. That is, every 18 months we are actually doubling the capability of fitting transistors on our chip, and because of that, what it means is that the chip can now perform many more complex operation. Okay, so just a simple understanding here is that we may start with something what we call is a basic algorithm. For example, our algorithm is as follows. Let's say A plus B, a very simple mathematical operation that we want to perform. Okay, and this algorithm may be written in some sort of computer language, let's say a C language. Okay, C programming or so this is what we call a high level algorithm or code. Okay, and this code is then translated into, let's say, our hardware circuit. Okay, so our hardware circuit may consist of things like, let's say we have A and B, and we get Y, and maybe we get a carry. Okay, so we may have some sort of a digital circuit, and this digital circuit is made up of gates. Okay, made up of gates. So I'm just putting some gates and so on. And the gates are made up of transistors, for example. Okay, so you have some transistors, let's say. Okay, and the transistors are made up of the device, right? So we have, let's say, drain, gate, and so on. Okay, and this is on the VLSI level, will be based on the metals and all the conduction materials used to create this what we call device, which is a gate. Okay, and then the gate is actually like this. This is actually sorry, this is a transistor, and transistor actually makes up the digital gates. The digital gates actually makes up the digital logic that we want to do, and the digital logic is actually representing some sort of algorithm. Okay, but obviously what it means is that if I can make these transistors smaller, what it means is that in the same, let's say 1 millimeter space, we can now put more transistors inside. And when you put more transistors inside, means that I can represent a more complex digital logic. So now I can do more complex operation in the same space. Okay, so the progress in computer technology, whether it is a display technology, whether it is graphics card, whether it is central processing unit or CPU, whether it's memory, and so on, or whether it's any kind of accelerator that you have on your computer, is all because thanks to the revolution in this IC design. Okay, so just we are able to do it because we're able to do complex things because now we can fit more transistors on the chip. Okay, because the technology supports that. Okay, so the Moore's law actually tells you that every 18 months we are going to double the we are able to double the number of transistors that we can fit on the chip. And you will be thinking, why? What does a transistor got to do with our computer technology? It's because of this, because all your logic gates at the end of the day just becomes transistors. Okay, of course they turn on and off at certain rate to build a gate and a circuit and an operation. Okay, and besides that, it allows us to do and apply computer technology in many different applications. Okay, one of it is very common, is that your handphone here, right? So this is actually computing technology. Okay, so you don't realize that actually a lot of computing technology is inside here. Okay, so a phone is basically a computer. Okay, and you will also not realize that actually you have computers in your automobiles. Okay, so when you drive a car, you have at least I don't know, maybe 30 microcontrollers or microprocessors in it. So you have a lot more embedded system in a car than you can realize. Okay, you have a controller for your airbag, you have a controller for your braking system, you have a controller for your in-car entertainment like radio and so on. You have a controller for your gearbox, you have a controller for your engine control unit, ECU, and so on. So you have a lot of microprocessors in your car, especially today. If you buy an autonomous car from Tesla and so on, then you'll have even more. Okay, and behind the scenes, you also interact with a lot of computers. Okay, you interact with you interact with servers. Okay, like today we're having this virtual class. Actually all my transmission and your transmission actually goes through the WebEx server. Okay, so my video and whatever I'm displaying actually goes to WebEx, and WebEx actually transmit it back to the 29 attendees we have today. Okay, so you use search engines and World Wide Web, those are all computers as well. So computers are pervasive, they are everywhere, and anything you pick up today will definitely will have some sort of a computing device. Okay, and we can definitely divide our computer classes into some categories. Okay, so we have the phones and tablets, and we call that the personal mobile devices. These are things that needs to wake up very quickly. It needs to be real time. It needs to be energy efficient, because for a typical phone, you want to use it for 1 day, 1.5 day without charging. You can't charge it every 1 hour. Okay, it can't be connected to the wall all the time. So things like tablets and phones are required to be energy efficient. Okay, while on the other hand, we have these desktop computers. So desktop computers, they are more focused towards performance. Okay, so you want to be cheap but high performance. So size is not really an issue. Power consumption is not really a big issue. It is still an issue, but not really a big issue. It's something that we can tolerate. But desktop computers is a class of what we call computers that's different than mobile devices. At the back end, we have servers. And servers, they have a different strategy. Servers, they need to be 100% all the time available. It needs to be scalable. It needs to have a high throughput. In other words, that the servers should be on or online all the time. It's not that I mean, if you have been online banking, suddenly you want to do online banking in the midnight, and you can't do it because this is in maintenance mode. That's not like a good experience to the user, right? You want to be something like email. You can check your email anytime. Okay, you can run your simulation anytime. So servers should be available all the time, should be scalable. Scalable means that as more users are using it, you should be able to increase the capability of the server easily. Okay, maybe like something like Lazada and Shopee. You may have, sometimes you have peak usage. A lot of people are using the online marketplace, and sometimes there are not many people using it. So you need to be able to scale depending on the demand, and also a huge throughput. Throughput means a lot of concurrent connections. Now, besides that, we also have clusters and warehouse scale computers, and this is actually to provide you software as a service. For example, if you have seen things like Google Drive, Google Compute, Microsoft Office 365 online, those things are all software as a service. Okay, so we have these clusters of computers to serve you certain service. Could be cloud storage, could be cloud computing, could be collaborative tools, and so on. So this one is another category of computers. And of course, one category that you don't really see all the time is embedded computers. So embedded computers are those that you don't really realize. You have them in your car, many of it. You have it in your air conditioning, your smart air conditioner. You have it in your smart watch. Um, you have it in your hard drive actually. Okay, if you purchase a solid state drive, there's a controller inside as well. So these are all what we call embedded computers. You don't see it, but it is there. Okay, it's running behind the scene. This is what we call the post-PC era. What it means is that normally PCs is the number one choice of computing platform, but in 10 years back, okay, what we have seen is that the growth of PC has been slowing down. At some point, actually dropped or stagnated, which is not increasing. What you see is a huge increase in tablets, okay, and then later a huge increase in smartphones. Okay, so you can go to any typical household and you'll see you'll have more tablets plus phones in the house rather than laptops and PCs. Okay, because phones and tablets are becoming the primary choice of computing for many users. Okay, why? Because it is compact. You can do a lot of things on it. It's cheap. So we call this era as a post PC era. Okay, that is more people are not using PC, but they are using phones and also tablets. And you can see here, tablets is also going down recently. Okay, not many people purchase tablets. The reason is because our phones are more capable than tablets. The screen is large enough. Okay, so there's no need to purchase another device. There's no need to have a tablet and a phone. A large phone is just like a tablet, so many people don't buy tablets anymore because the phone itself is sufficiently replacing the tablet. Now, if you look in a typical computing device, for example, this is the iPad. What you can see is that we have a couple of components. A typical computer will have three important components. Okay, the first is called the processing unit. Okay, the processing unit. So in this picture, this is the processing unit, the A5, Apple's A5 chip. Okay, so this is where all the processing is performed. For example, if you want to add two numbers, if you want to divide something, if you want to move data, it's all done inside this processing part. This is just like our brain, okay, where all the processing happens. The second component is actually the memory. Okay, the memory. So I believe this Toshiba chip here is the memory module, but I could be wrong. But let's just assume that this is actually the memory module. Okay, so in any typical computing device, you will have memory. Just like ourselves, we also have memory somewhere up here, because our brain, our processing, and memory is next to next. Okay, okay, so we have memory as well on the computing device to store our data, to store our program. Okay, so that's very crucial as well. Number three is actually the I/O. The I/O means the input output, which means how you communicate to the computer. So here you can see here we have the touch screen. This is a touch screen. Sorry, the touch screen where you can perform some input and output. You can see something on the screen, that's an output. You can touch the screen, that's an input. And of course, you may have a physical button here as well. I think the iPad has one physical button, that's an input as well. Then you have a camera, that's an input as well. You may have some speakers. I don't know where they put the speakers, maybe here. Okay, so that's an output. And of course, not forgetting, we also have things like this. This you can see, this is a, I think this is a Broadcom logo. Okay, this is actually the Wi-Fi of 3G modem and so on. That's also input output, a communication device inside your iPad. Okay, Bluetooth, Wi-Fi, 3G, 4G modem, those things are also called I/O. And finally, I mentioned three things, but there's another fourth element, which is called the bus. Okay, so all of these things are connected through some bus. Okay, so you have the CPU, you have some memory, you have some I/O. Okay, so these things are connected through some bus. Okay, so data bus, control bus, address bus. So there must be some connection between these things. That's actually the fourth element of any computing device. So it's same to us. The processing is our brain. The memory is also close to our brain. We have a separate component in our brain that stores information. Our I/O is including mouth, nose, ear, eyes. Those are all of our I/O. And the bus is our central nervous system. Okay, the central nervous system is where all our information, electrical signal goes through our body. Okay, just 1 second, please. All right, so same with us. So all of these things are okay in our computing device. Okay, if you see here, of course, for a typical computer, okay, we have of course some other supporting things as well. We have can't see it here, but probably there's a power driver here. Okay, power driver somewhere around here. I'm not sure, maybe here. Okay, I'm not sure for here. A power, that is the power circuitry, that is for you to charge the device. And you can see some power modules here. This is actually the battery, and depending on your device, you may have this as well. And if you look at this picture, our computing memory is and communication is very small, a very small aspect of our device. The bigger aspect is actually the touch screen. Okay, and also the battery modules at the back of the iPad. Okay, so when you look into the processor, which is our primary concern in this class, our primary concerns in this class are actually the processor and the memory. Okay, these are the two important things that we are going to look throughout this lecture. Okay, not today obviously, but throughout this semester. Okay, so what's inside the processor? So this is actually quite kind of a secret. Okay, basically. Apple does not disclose everything what's inside their processor, but let's just have a look at what you have inside the processor. So this is a bit of background. Okay, so what you have in a typical computing device is that you have what we call a processor. So let me draw that. Okay, and we call this the central processing unit. Okay, this is the primary component of our what we call a computer, and this actually communicates to some storage memory, and this is what we call the memory. So we have some memory here. Okay, and our memory will contain a couple of different things. Okay, but primarily we can just divide it into two components. One is called the data memory, and the other one is called the code memory. Okay, or instruction memory. Okay, instruction memory. Okay, so what's the difference between data and code? You can just imagine this as Photoshop. If you have used Adobe Photoshop, Photoshop is your code, your program. Or you have used Microsoft Word. So Microsoft Word is the code, the program. But the Word document or your JPEG file is actually your data. Okay, so data is actually the thing that you're working on. Okay, so same thing in our memory, we're going to have data as well as code. Okay, and obviously these two things need to communicate to each other. So we're going to have some connection between these two things, and we call this the bus. Okay, and if you're transferring data over this, we call this the data bus. Okay, the data bus is for you to transfer data to the processor. Okay, and of course, this memory is large, and there are a lot of things inside this memory. So there must be a specific location in memory where you want to load something. Okay, so the memory will have an address. Okay, okay, and for example, the memory is actually so let's say we have the memory, and the memory has a 16-bit address. Okay, 16. Let's just put a more realistic number. The memory is actually a 32-bit memory address. 32-bit. What it means is that the CPU can provide a 32-bit address over the address bus. Okay, so the address bus is just like a phone number. Okay, so if you have a 10-digit phone number, then you can have 10 digit of unique addresses or phone numbers. You can have a 0000 all the way to 99999. So it is something like that. So if I have a 32-bit address, then the first address will be in hexadecimal 00000000, and the final address will be in hexadecimal FFFF and FFFF. Okay, so that's going to be our address range. Okay, and if you look all the way from here to here, the total addressable memory is 2 to the power of 32, which is 4 gigabytes of memory. If one location you can store one byte. Okay, so how can I access any location in this memory space is by giving the appropriate address, and then we will go to that address to get the data in. Okay, so that's how actually the CPU accesses data from your data memory. And so what's important here is the address. Okay, great. Now, how much data I can bring in and at any one time? How much data I can bring in at any one time? That really actually depends on the size of my data bus. So if my size of my data bus is 16 bits, what it means is that at any one cycle, I can bring in 2 bytes of data. Okay, 2 bytes of data. So the data bus width tells you the size of the highway of how much data that can be bring in and out. And that's where you can see here the arrow is in and out, while the address only has arrow going out, because only the CPU can determine the address. Okay, so that's the basic concept we are starting to build on. Okay, the next important thing here is that your program, your program that you want to execute actually is stored inside my code memory. And where is my current program really depends on what we call the program counter. So on the CPU, we have one special register called the program counter. The program counter tells me or tells the system where is the next address I need to fetch my code. Okay, I need to fetch my code. Okay, and this code that I want to fetch in will go into the CPU into what's called the instruction register. Okay, so in our system, we're going to have two components. We have the data, we also have the program. So I need to load the program, I also need to load the data. So these are the two things that I need to continuously do on my CPU. Okay, so how do I load the data is through the data bus and also the address bus. It tells me where to go. While how do I load the instruction is we load the instruction by looking at the program counter. The program counter tells me which address I need to go to fetch the instruction, and the instruction will go into the CPU into the instruction register. And what's a register? A register is like a high-speed memory inside your CPU. Okay, a high-speed memory inside CPU is called the instruction register. It's called the register, sorry. It's a place for you to keep things inside the CPU. All right, great. So let me further expand this explanation. Okay, so this will be our base understanding. Okay, so that other materials will be based on this basic understanding here. All right. What else? So in order for me to keep more things in the CPU, a typical CPU will have many registers. So we have register 1, register 2, register 32, 31, for example, register 0, 1 until 31, for example. And this is what we call the register file. A register file means that the available slots of registers inside, the collection of registers inside CPU is called the register file. Okay, and because you may be fetching the value of A into the CPU, fetch the value of B into the CPU, and A plus B, you get C. So where should I keep A? Where should I keep B? Where should I keep the answer C? So all of those things will be inside your register file. All right, so now where can I perform this operation? So the operation is normally performed by what's called the arithmetic and logic unit. Okay, so data from the register will go here. Okay, and it will be written back here, for example. Okay, and this all operations such as add, multiply, subtract, and so on. Okay, is done by the arithmetic and logic unit. Okay, and finally, sometimes the CPU will be giving you some information. For example, the answer is negative, or the answer is 0, or the answer generated a carry, or the answer generated an overflow. So this is what we call the status flags. Okay, the status flag. So let me draw a flag there. Okay, so that's a status flag. Okay, a status flag tells you the current status of the CPU. So that's actually how a typical CPU will work on. So a CPU is basically a state machine. So what is the state? So the state CPU will basically look at the program counter. It will go to the code memory, instruction memory. It's going to fetch the instruction, Then it is going to increment the program counter to the next address. Okay, then it's going to fetch any data if required, fetch data. It's going to execute, and then it's going to repeat this process many times. Okay, so typically that's going to be the steps. You're going to go to your code memory, you're going to fetch an instruction. The instruction goes here and gets decoded, and then it's going to go to the data memory to fetch any required data, and then it's going to go sorry, could be the register, right? Could be register, and then after that it's going to perform some ALU operation. Then it's going to write the data and increment the program counter to go to the next address. So a CPU is basically just a state machine that's repeating itself many times. All right, so let's expand this knowledge a little bit more. Okay, what if I have what if you have more than one CPU? Okay, so if you have more than one CPU, what's going to happen here is that, sorry, if you have more than one CPU, just drag this. Okay, if you have more than one CPU, what's going to happen here is that, just 1 second, please. Okay, so if you have more than one CPU, what's going to happen here is that we're just going to copy this CPU and put it here, CPU 2. Okay, that's going to be our typical approach for multi-processor or multi-core. So of course, we're going to have the same things inside the second CPU. Okay, okay, we have the same things here. Okay, and we're just going to copy that. So if you have a quad core system, you have 4 cores or 4 processors, basically you copy paste this core. So this is what we call the CPU core. Okay, of course, I'm oversimplifying the explanation for today. When you do copy and paste, of course, you have to do certain kind of, um, certain kind. I mean, it's not exactly 100% copy and paste. There's going to be some things that you have to do additionally. Okay, but generally the idea is just to duplicate this core in our design. Okay, now let me add a little bit more explanation here. In most cases, what you're going to see here is that the uh, the uh, the communication to the memory is taking too much time. So since our CPU is running at high clock speeds, let's say 1 GHz, okay, but the memory is significantly slower. Even though the memory is running at megahertz, but still you're going to have a lot of clock cycles to, to wait for the data to come in. So in order to speed up this thing, typically what we're going to have is that in many of our application, we are going to introduce in between what we call is a cache memory, cache, cache memory. Okay, okay, so we're going to have a cache memory for data, so we can cache the data, and we're going to have a cache memory here for our instruction. We call this instruction cache and data cache. Okay? This is actually to introduce a faster memory in between our processor and our slow main memory. Okay, so that's actually how generally the CPU working looks like. Let's see, did I miss anything else? Um, Loman, buka kipas. Okay, so that's actually how this basically the CPU looks like. I'm just thinking if I miss anything here that I could, point out right now. Mm, we have the CPU instruction register. Okay, all right. So that's actually the basic workings of the CPU. And just 1 second, please. The kids are disturbing. Okay, sorry for the interruption. Okay, so coming back to this one, how does everything work? Okay, so let me give you a general explanation. So typically, we are going to start with a problem. These are all general. Later, when we go back to the slides, you can see how it relates. Okay, so typically we'll start with some algorithm. Okay, we have some problem. Okay, some problem that we want to solve, and this, of course, we're using a computing device, so the problem is solved in terms of an algorithm. Okay, so what is an algorithm? So algorithms is basically a step-by-step approach to solve our problem. Okay, so things like bubble sort algorithm, you know, machine learning algorithm, those are just basically step-by-step instructions on how to solve something. Basically, it's just a recipe of how to solve something. So let me just give you an example of a very simple operation. So let's say I have a very simple algorithm where I want to say I want y equals to mx plus c. So this is actually our algorithm that I want to solve. Of course, this is just a mathematical representation, and sometimes algorithms are represented in terms of pseudocode, SPSEUDO code. Okay, pseudocode begin, do, while. Okay, sometimes algorithms are mentioned in terms of pseudocode. Okay, Okay, for example, sometimes algorithms are shown in terms of flowchart. I don't know, something like this. Sorry, M. Just give you some. Uh, this has nothing to do with this, okay? But just to show you how algorithms may be represented in terms of a flowchart, in terms of pseudocode, and so on. Okay, so really, it really doesn't matter. What it matters is that we have some problem that we want to solve using a computer. So typically, this solution can be solved in a couple of different ways. We can buy some discrete components. We can buy an adder circuit. We can buy a multiplier circuit. Okay, so this is an adder circuit. This is a multiplier circuit, and we can put some inputs coming in. Okay, this is the M, X, and C. Okay, and then we can create our own circuit to get our answer. That could be one solution using discrete components. Okay, or we can design our own chip. Okay, we can design our own chip. So we can design our own chip. And of course, inside this, we have the logic gates, detailed logic gates, of course. Okay. And this can be implemented on our field programmable gate array, or we can create our custom chip on our application specific IC. That could be another solution. Okay. Or this third solution is to use a programmable CPU. Okay, what is a programmable CPU? Is that what it means is that now this algorithm here is now converted into a code. That's why a CPU is called a programmable machine, a programmable chip. So what I'm going to do is I'm going to take this algorithm here and I'm going to write the code and use it. So it really depends on the language of choice. Okay, and I believe you are very well versed in many languages. Some of you are good at C, C++, Java. Nowadays people use Python, MATLAB, Perl, Tickle. I think TK, Tickle. This time I'm not too sure. Maybe you are expert on this. I am completely zero on Tickle scripting and so on. So there are many different languages. So you're going to translate your solution to your problem into a programmable code. Okay, so let's try to solve this, let's say, with the C language. So of course the syntax is going to be a bit different. Okay, then you're going to declare the variables 9, for example, with semicolon, C equals to -5 semicolon, and then the code is Y equals to M multiply with X plus C semicolon. So you can see that the algorithm may be different due to the language. So here in math, you can see it's written this way. Okay, but in our programming language, you may have to write it in a different way. Okay. All right, so this is the language. We call this as high level language, this whole thing. High level language could be C, C++, Java, MATLAB, whatever preferred programming language you have or you want. But of course, in this class, we're going to focus on basic C. Okay, so this is called the high level language, and this needs to run on the CPU. So this code will go to what we call a compiler. A compiler. What is the purpose of a compiler? The purpose of the compiler is to convert this high level language into a low level code. Okay, a low level code, or we call this as the assembly code. Okay, so the assembly code is what the CPU can perform. So the assembly code will tell, basically this tells you Y equals to mx plus c, mx m multiplied by x plus c. So this needs to be converted into some operations on the CPU. So you can see this is just one line. Okay, but this may be converted into, let's say, load a data into register 1 from some memory address. This is my X. Then load another data into register 2 from some memory location, and this is my M. Then load another data into another register, that is my C, into R3. Then M multiplied by X, so multiply R4, M and X is R2 with R3. Okay, then add the result R4 with C. C is M and X, one, this R2 and R1, R3. Okay, then store the data back to store my data back to some memory location called Y. For example, So here what you can see is that the purpose of this compiler, okay, is actually to translate this high level language into some low level code. And what is so important here is that if you look inside this low level code, there is some mentioning of the registers, there is some mentioning of the instruction. So here there are two important things that you must realize is that the job of the compiler is not only to convert, it also to determine the registers or the low level details of the CPU as well as the instructions that needs to be used. So this, what are the instructions that we can use? Really depends on my CPU. Here's my CPU. Really depends on my CPU, and we call this the instruction set architecture. Okay, the instruction set architecture will tell you what is the CPU capable of doing. Okay, because if you look inside the high level code, there's no mention of the specific low level instruction. There's no mention of the specific registers that we are going to use. We just say MX plus C. But on the actual hardware, we need to know what are the registers that we need to use. And this really depends on the CPU. So the generated code here, okay, the generated code here depends on the compiler plus the CPU instruction set architecture. Okay, it depends on that. So if I take the same code, okay, and I compile it, and this compiler is for the Intel architecture x86, okay, and this is for RISC-V, then the generated code will be different. You'll have EAX, EBX, those are the registers on the Intel CPU. Okay, so you're going to have different generated code because the Intel CPU has a different instruction set, it can do different things. Okay, so the high level code is the same, but the low level code will be different. So the benefit of high level code is that I can write it once and compile it for different platform. I can write y equals mx plus c, and I can compile for Intel, I can compile for ARM, I can compile for RISC-V, I can compile for different targets, no problem, as long as I have a compiler. But if I write a code in assembly, then this code can only run on one CPU. Okay, if I want to use the same code on the Intel chip, then good luck, you have to rewrite again, because the Intel chip will have different naming convention for the registers and different instructions available. So that's why we use a compiler to convert high level to low level. Okay, finally, the story doesn't end there. Okay, if you further look at this, each of these code here cannot be executed by the CPU. It still needs to be converted into the binary representation. Let me just quickly write that. Okay, and I hope you just understand what I mean. So each of these code here is going to generate some binary code for it. Okay, so typically on a reduced instruction set computer, the instruction generated will have the same length. Okay, which means that a store or an add or a multiply or a load will all have the same binary code length, while such as the Intel CPU, which is called as the complex instruction set computing or computer, will have variable length. Variable length means that different instruction will generate different code. So for example, a branch will generate an 8-bit code. Okay, an add will generate, let's say, a 16-bit code. Okay, a multiply will generate a 48-bit code, for example. Okay, for example, so it will have a varying length of instruction generated. Okay, so coming back to this one, what it means is that, for example, this is a 32-bit code. 32-bit code. So when this is compiled, it is going to generate a 32-bit binary code. So store is a specific operation, so it will have its specific code 011011011010111, a 32-bit specific code. So that's what it's going to generate. Of course, a 32-bit code, binary code, is very hard to write. So we typically write it into a specific shorthand hexadecimal. So this is a 32-bit hexadecimal, FEEDAAAAB, for example. This is a specific code for this in hexadecimal. All right. So this code, for every line here, For every line here, it's going to generate one code like this. And this code is what we call your instruction or your program. And this instruction is, let me just move this. Where is it? Coming up. Okay, it's too far away. That instruction is here. Okay, so that is actually your instruction. Okay, and when you fetch the instruction, it'll go in here, then the instruction is decoded to understand what you need to do. And it will tell the decoding, it will tell the ALU, oh, you want to do add, oh, you want to do multiply, oh, you want to do something. So that's actually decoded from this instruction that comes from our high level language code. All right. Now, finally, maybe this could be the last thing for this slide. If I remember more things, I will revisit this diagram here. Okay, but as of now, I can't remember anything else I want to mention. I think it's pretty much complete. The other thing is that what is the size of the data that we can process here? Remember, the data is going inside my ALU, okay, to perform addition and so on. So what's the size of the data coming in? What is this size? So this size is what we call the CPU size. Okay, so this size is what we call the CPU size. Okay, so if I say I have an Intel Core i5 8550 Ultra Mobile chip, which is a 64-bit processor, what it means is that the ALU can receive 64-bit number, and produce a 64-bit answer. Okay, so that's what it means. So if I have a 32-bit CPU, then the input will be a 32-bit and a 32-bit into the CPU. Now, how much memory I can address? How much memory I can address depends on my address bus. So if my address bus here, okay, has a size of, let's say, the size is 8-bit address bus, then the maximum memory I can access is 2 to the power 8, which is 2 to the power 8 is 256 bytes of memory. If I have a 16-bit address bus, then it's 2 to the power 16, which is 16 kilobytes of memory. Okay, if I have a 24-bit address bus, 2 to the power 24 is 32 megabyte of memory. I think if my calculation is right, if not, you just try with your calculator. Okay, and if I have a 32-bit, then 2 to the power 32 is 4 gigabytes of memory. Of course, be very careful. 1 byte is 8 bits. 1 kilobyte, or sometimes in most technical books it's written as 1 ki byte, okay, key byte, okay, to avoid confusion with the normal kilo that we have, 1 kilogram. To avoid the confusion, they write 1 key, 1 kilobyte, okay. But I will just use 1 k byte, okay. That's the typical way. Is actually 2 to the power of 10, which is 1024 bytes. Okay, and let me extend that a little bit here. 1 megabyte is simply 2 to the power of 10 kilo. That is 1024 kilobytes. Okay, so just to give you a correct understanding here, so let me just launch this. Let me just go to, it's okay, we can use this. Let's say we have 24-bit. So 2 to the power, where's my power? Oh no, I need to go scientific. Okay, 2 to the power, just power of 24. You can see that 16,776 bytes. So this is actually 16,776, 216 bytes. Okay, but this is actually divide by 1024, and this will give you in kilobytes. Divide by 1024 will give you in megabytes. So it's exactly 16 megabytes. Okay, so that's a unit conversion. So I believe 1 kilo is 1000, right? But in our computing, 1 kilo is 1024, just to be safe there. All right, so yeah, so that's actually how basically a CPU works in a nutshell. So for those who have not taken any microprocessor class, or haven't taken any computer architecture class, or haven't taken any C class. That's basically all the mixture of everything. You can see that how the high level code we have. We always start with some problem, okay, and you derive a solution, and then we want the computer to do the solution for us, so we write the program in C and whatever language you like, and then that needs to be executed on the hardware. That means it needs to be compiled to generate the assembly code, and then the assembly code converts into the binary representation, and that binary representation actually goes in our code memory, and the CPU will fetch this instruction and decode and execute and write back the memory and repeat this many times. All right. Okay, so that's basically the understanding that we need to know. Okay, of course, since I saw this slide here, so what you can see here is we have data path, control, cache, and I/O. So I think I've covered all of those things already. I've shown you the cache memory. I've shown you the data path. You have some control signals, okay, which I've not shown here right yet. Okay, but there's also another important thing to mention here. In today's devices, okay, what we have is most likely a system on chip. Okay, what is a system on chip? A system on chip is a single chip. A single chip here, and inside a single chip we have CPU, maybe many CPUs. Okay, and then we also have some other things as well. We have some I/O controllers. We may have a Wi-Fi modem. We may have a DDR memory controller. Okay, we may have other chips as well. We may have AES encryption chip. We may have a image signal processor. We may have a digital signal processor. We may have a big GPU. We may have some big cache memory, and so on. So typically today, if you buy a modern chip, for example, a Snapdragon 888 by Qualcomm, okay, for example, a chip for the mobile usage, what you'll see is that it's actually not just a processor inside that. We have a lot more components inside that, and so a Snapdragon 888 is actually a system on chip. It's not just a processor. We don't call it a microprocessor. It's not a microprocessor. It has a lot more things inside. It's a microprocessor, many of it, maybe quad microprocessor with I/O, with Wi-Fi, with GPU, with DSP, with ISP, with encryption, all sort of things inside that. We call that a system on chip. Okay. Okay. So all right. So let me cover a few more slides before I give you a break. Okay, so let's just have a look at quickly look at this Apple's A5 chip here in the slide. And based on from our understanding, it's very easy to see. We have some CPU cores there, the ARM microprocessor core inside. We have some processor data path here. We have some GPIO. We have some other digital logic, which is secret. We have some DDR memory controller, and actually they have other things like signal processing, image signal processing, video compressor, video decompressor, blah blah blah. So they have a lot of other things. So this is actually the what we call a kind of system on chip. Okay, so this is what I was telling you about. What we have is at the top is that we write our program in high level language because it is easy to express and easy to migrate. Okay, we call that portable. Okay, portable doesn't mean that a phone is portable, you can bring here and there. Portable for us, what it means is that our program is portable, means that the program is written in high level language. I can take the code and compile it for any target. Okay, I can take the C code and I can compile for iOS. I can take the C code, compile for Android. I can take the C code and compile it for Windows. I can take a C code, compile for Linux for x86. So I can take the same code and portable. That's what the portable means in our class. Okay, not portable means bring it here and there. Okay, so writing in high level language is easy to express and easy for us to port to different platforms. And we use a compiler to translate the high level to machine code. And of course, we have some operating system. The purpose of operating system is to manage the resources. Why do we have Windows? Why do we have Linux? Why do we have Android OS? It's because to a system to manage who gets to read the data from the drive, who gets to execute on the CPU, how much memory your program is allowed to use. So somebody needs to manage all of these things, handling IO, managing memory, scheduling tasks, which program runs first. That's actually done by the OS. Okay, and of course at the lower level is where you have the processor, the memory, and the IO controllers. Okay, this is what I was explaining to you. So we have a high level language which gives you abstraction. Abstraction means that we decouple ourselves from low level details. That's what we call abstraction. Okay, basically what it means is that we try to keep things as simple as possible. Okay, if I ask you to go and eat, okay, you if you want to explain how to eat to a small kid, it's just very simple. Take the food, put in your mouth, and then munch the food, and then swallow it inside. As simple as that. Okay, abstracted. You're not going to explain the lower details that it will go through your esophagus, or it will go through your stomach, and then you're going to have acids there, and then it will go to your intestines, and you don't need to know those details. Okay, because you're just telling a small kid. So it's just like that. A high level language code means that we want to abstract from the details. Okay, which is good. In some sense, it's good. Why? We want the compiler to handle the low level details. Okay, we would want to clutter our mind to think too much. So if you go back to my explanation here, you can see how much the difference is between high level and low level. Algorithm is this. See, one line only is the algorithm. Okay, written in a C code, a bit more longer, one line of code, two, three, four lines of code, plus one, five lines of code, a little bit more complex. If you go to a low level details, you have more instructions, 1, 2, 3, 4, 5, 6. There are a lot more instructions, a lot more details that needs to be known. Okay, so abstraction means that you just think about it at the high level. Of course, what actually happens is that it's been converted to the machine's ISA. Like I mentioned to you, this is the ISA. ISA means what the CPU can do, the exact instructions the CPU can do. Okay, so there are some things you don't understand in the English language. The English language perhaps has 4,000 words, 5,000 words. I'm not sure, but probably your vocabulary is just 1,000. Those are the common things you talk, or you say, or you read. But there are some words you do not know. So those words that you do not know it's not in your ISA. Okay, it's not in your instruction set. Okay, if I mention it to you, you won't understand. Okay. Now, of course, I also mentioned to you that finally it gets converted into this binary code, and this is actually what happens. You can just imagine it with your phone here. So you have your phone here. Imagine you want to call me. Okay, so what you're going to do is that you're going to find my name in your address book, Osman, and then you're just going to press the call button. Gone are the days where you remember phone numbers. You don't really care what is my phone number. It's in the address book. That's all that matters. So if I ask you, do you know my phone number? For sure, you do not know. What you know is that in the phone book, there is Osman. And when you press the call, the compiler okay, the address, the phone call app actually converts Osman into 01970553336 and uses that to call me. So you don't see that number. Okay, it is done behind the scene. It's the same thing here. We don't really care about the binary code there. What we care is actually the high level, because the binary code is going to be generated by our compiler plus assembler. Unless you are the person who's writing the assembler, you're writing the compiler, then you need to know the binary code, because you are designing the tool to perform the compilation. Okay. We're at slide number 9. Okay, so why don't I give you a 5 minutes break, and I'll see you at 10:33. All right, see you in 5 minutes. All right. Okay. So in the past, when we look at the computer architecture, what we mention is just the ISA. Okay. So in the past, when you say, "Hey, computer architecture," what it means the instruction set architecture. So what's the instruction set architecture? It tells you what are the available instructions on the CPU, the available registers. Okay, and things like memory addressing, operands, how the control flow instruction, and how we encode the instruction into the binary code. So these are all the things we call as ISA in the past. Okay. However, the real computer architecture, we also want to look at the specific requirements of the target machine and how to design and maximize the performance in terms of cost, because cost is very important, money, power consumption, and also availability. Okay, this also includes our instruction set architecture and our micro architecture and also our hardware. So today in this class, we're also going to look not only at the ISA, what are the instructions, but also at the internal micro architecture. Okay, so when you talk about performance, we have to look at all the different aspects. The first thing is, of course, the algorithm. Okay, the algorithm actually determines how many number of operations that we are going to execute. So, what is an algorithm? Algorithm is basically a general solution to a problem. So that's what we call an algorithm. It's a general solution to a problem. So, for example, how do I get from A to B? Okay, how do I get from A to B? So we have a location A and we have a location B. How do I get from A to B? So the mapping app may provide you one route here, may provide you a different route here, may provide you a different route here. So it may provide you three different routes to arrive to your destination. Okay, so algorithm tells you the solution. Okay, and of course there are different algorithms to do the same thing. Okay, different algorithms to do the same thing. For example, I want to search for Usman. Or let's say I want to search for. Let's give it a look. Okay, so let's open a browser and let's go to google.com. Okay, and let's search for, let's say, Mahathir. Okay, so that's Mahathir. So we have the Wikipedia comes first, followed by Twitter. And let's go to another search engines, for example, Bing. Okay, and okay, and let's search for Mahathir again. And you'll see the results are different. It comes with Wiki, and followed by what? Comes with the SCMP news, comes with Free Malaysia news, comes with videos, Malay Mail, The Star. Where is his Twitter? So his Twitter doesn't appear. Okay, so you can see that how come I search for the same thing on two different search engines, but the results are in different order. So of course, you may argue that the data that they have, okay, the data that they have is actually different. That could be, but assuming the data is the same, how come we have a different search result ranking? This is what we call algorithm. Okay, algorithm means how to solve the same problem, for example. Or if you want to sort numbers, so let's see sorting algorithms. Okay, so you can see there are so many different algorithms to sort numbers. So if I have a list and I want to sort it from A to Z, there are different ways of sorting it. Okay, you can use bubble sort, you can use quick sort, you can use binary search sort, you can use merge sort, insertion sort, selection sort. So these are all different algorithms to do sorting, and they operate. You will get the same result at the end of the day. That is sorted number from small to big. But the way, the process to achieve the result is different. Some are faster, some are slower, some use more memory, some use less memory, and so on. So that's what we call algorithm. Okay, so the performance always starts with the algorithm. What I'm trying to say is that if your solution is poor solution, you give me a poor solution, the mathematical solution is poor, means in terms it's slow, a lot of steps to be done, then even if you use a fast processor, you're still going to get slow results. So sometimes it's not the problem of the processor, it's not the problem of the memory system, it's the problem in the algorithm. Okay, so it's like giving 100 CPUs also, you're not going to get the performance because it is slow. Next is actually the programming language. Okay, it's the programming language. Okay, so the programming language and the compiler is going to help you generate the machine code. Okay, so let me go back to this. If you can see here, I have the following code. Okay, the following code that actually being converted into the following machine or the assembly code. So it really depends. So if it's a intelligent compiler, okay, and you're trying to do this, okay, and the value of M is 10, the value of X is 4, the value of C is 0, for example. Okay, so the an intelligent compiler will see that what you're trying to do is is going to be converted into logical shift left by 2 bits. Okay, it's just going to do that. Okay, so instead of using a slower multiplication operation, the compiler can just convert it into a bit shift that
Doctor, you
okay,
still
yeah,
there?
yeah. Is it clear now?
Yes.
It says that you are dropping. Okay, now it's okay.
Yes, it's okay now.
Okay, okay. I'm not sure what happened. Okay, okay. Anyway, if you have an issue, just put it in the chat. So I saw some chat popping up just now. Okay, all right. Okay, now it's okay. Aisha, go there. Missing. Go there. Okay, thank you. Okay, so if you have CPU B, for example, and the CPU B does not have the divide instruction. So what does the CPU got to do? So the compiler. So it's, again, the compiler will have to match or convert this code depending on what's available on the ISA. Okay. So if the ISA supports divide, it can simply take this and use divide. If there's no divide, then this will probably be changed into multiple subtraction. Okay. For example. Okay. And let's say the result is X. You have to do multiple subtraction because division is actually subtraction. So depending on what's available on the hardware, the compiler will have to do some sort of translation. So if the hardware does not support multiply, then you have to do add and shift, for example. If the hardware does not support divide, then I have to substitute it with a subtract operation, and the code become longer and slower. Okay, so it really depends on that. And of course, a more intelligent compiler will say 100 divided by 4 is simply 100 shift right by 2. So I can just use logical shift right to perform the division. So it really depends how the compiler is going to do the optimization, but it depends on what the ISA can do. So I guess you can just assume it this way. There are some terms in your language. I have some Indian students here, some Chinese, some Malay, some local Indians perhaps, okay, Malaysian Indians, and so on. So you may have some terms that it's only one word for you. Okay, for example, I can just say, hey, you can just tell your foreign friend, hey, durian. Okay, if you mention durian to any Malaysian, okay, any Malaysian, so the Malaysian will know what is a durian. But imagine you want to explain this to a foreigner, okay, who is not a Malaysian, then it becomes multiple words of explanation. You have to explain that it is a thorny fruit, okay, the color is green, and then it has the fruit inside is yellow, okay, and the smell is from hell, okay, okay, and then but the taste is from heaven, okay, and that's the fruit. You have to explain in so many words, right? So that's what I'm trying to say. Just because you have a high level code in one line, when you want to translate to get an efficient performance, really depends on what CPU you have, how good is the compiler, what the CPU can do. Okay, so maybe the CPU cannot do divide. I mean, I cannot match divide instruction. You don't support it, so the compiler will do substitution with other operation. Okay, all right. Okay, now okay already. Okay, Yeah, so it all depends on what the architecture we have. Next is how fast the CPU can perform and how fast you can talk to the memory. That is actually also contributes to our performance, and our I/O system, including OS, will also determine our speed of execution. So let's have a quick look here. Okay, so if I go back here, okay, so where is my CPU? Okay, so if you look here, some of the things that affects our CPU performance is actually the clock rate. There are many, but it's at the clock rate. Okay, that is the gigahertz of your CPU. So that is actually going to tell you how fast you're going to execute the instruction. One of the parameters. Then of course your memory bandwidth. Okay, is also going to mention to are going to help you tell you how fast you can access the memory and bring the data in. And if you're talking to the I/O will also affect your performance. The I/O includes your Wi-Fi, your solid state drive, okay? And what are the things you have? Your touch screen. Okay, some touch screens they have 90 hertz, 120 hertz touch response. So those are the things that's going to affect your performance as well. Okay, so that's what I'm trying to say here. The performance depends on the choice of algorithm, the choice of programming language, how good the compiler is, the architecture on the CPU, how fast is your processor, how fast is your memory system, and how fast you can talk to your I/O. All of these things combined is going to, contribute to the performance of your system. Of course, I mean, you can just have a look at a very simple example, talking about the performance of a car. Okay, performance of a car. So this is how my car looks like. Okay, here's smoke. Okay, so how far the performance of the car really depends on a lot of things. It depends on the horsepower it is generated, depends on the liter of the engine. That's not sufficient. It also depends on your weight. You may be generating 750 brake horsepower, but you're actually a very heavy car, 2000 kg, for example. It really depends on the horsepower, weight, the engine capacity. Also depends on the aerodynamics, okay, and a couple of other parameters as well. So it's not just one parameter, it's a combination of everything that depends the performance. Now, we have some 8 great ideas. The first one is a design for Moore's law. Like I've mentioned to you, the Moore's law simply tells you that we are targeting that, we are hoping that more and more transistors are actually fitting on the chip so we can do more and more complex things in the future. So Moore's law says that the transistor doubles every 18 months on our chip. So let's say, what is Moore's law? So you can just have a quick read here. The principle that speed and capability of computers can be expected to double every 18 months. Like here it says 2 years, but I think it's 18 months, okay, as a result of increases in the number of transistors in a chip that you can contain. Why does it say 2 years? I thought it was 18 months. Maybe I'm wrong also, okay? I've been thinking it always mentions every 18 months, 1.5 years, but it says 2 years, 2 years, 2 years. Okay lah, fine lah. So you double the transistors every 2 years, which allows you to do more capable things on the chip. So we want to design our platform, we want to design our application for that purpose, okay? The next good idea is to perform abstraction. Abstraction means that we work on high level rather than low level. Okay, why? So that we allow compilers to do the job to perform the best of what is the best choice at the low level. That's one reason. The other reason, if I work on the high level, okay, I can do a lot more complex things at the low level. So at the high level, I just say A plus B. In the low level, today it could be an adder. Okay, in the future, I could have a turbo adder. Okay, even faster adder, for example. So the program really doesn't care what's at the low level. Okay, so as a programmer, we just look at A plus B, but in the low level, as a hardware designer, I can always change the implementation in the future without affecting my program. Okay, so this gives me a flexibility. Okay, abstraction gives me the flexibility on either side of the programmer side and also at the hardware side, that I can actually improve the lower level algorithms without affecting the higher level. Because I never promised to you to give you a regular adder. I never promised to give you a turbo adder. I just say that you can perform add. How the add is actually going to be implemented, whether in parallel or serial, you don't have to know. Okay, so that gives us flexibility and simplifies our design. The next one is make common case fast. This is another idea that we need to apply. So if you want to make something fast, okay, look at where most of the things are actually being used. Okay. So if you are using Microsoft Windows or if you're using Microsoft Word, what are the common things people use? In Word, people normally type, insert picture, save to PDF, insert tables. These are the common things people do. Things which are sometimes uncommon, including creating table of contents, creating mail merge, comparing two documents, those are less common, okay, less common. So if I really want to improve the performance of Microsoft Word, I should focus on the common case. Okay, so this way it will give the most benefit. Okay, so maybe we can also look at this in another way. It's called the Pareto's principle. It says that in many outcomes, 80% of the consequences come from 20% of the cases. So in programming, what it means is that 80% of your performance is coming from 20% of the regularly executed code. So focus on the 20% which is heavy usage. That's going to give you an 80% improvement in your program. Okay. In other words, I can just put in a general philosophy. If you look at your life and you try to see that you're wasting a lot of time, wasting a lot of money or whatever, and you want to optimize your time or money, you see that where is the most 20% of your money being spent, or where is the most 20% of your time is being spent. Optimize that 20% is going to contribute 80% of improvement in your daily life, for example. Okay, so you can read a bit more on Pareto's principle. In programming, it's the same thing, that 20% of our code is basically contributing to 80% of our performance. Next is to perform things in parallel. This is really fantastic, and we can see this today already. We have a lot of our CPUs in multi-core. Okay, multi-core, dual-core, quad-core, octa-core, and so on. So why? Because when you do things in parallel, what it means is that things happen at the same time, but multiple things. For example, driving and talking on the phone. Okay, that's a very bad example, but that's one way of doing parallel. Okay, you're driving your car, you're going through your journey and talking on the phone, which is a bad thing, but you're doing two things at the same time. You're saving time. Okay, what else? I mean, a lot of things you can do in parallel, right? So parallel. Just look at the bigger picture. You know why we have so much advancement in this world? Is because we have 4 billion people. We have 7 billion people on Earth. What it means is that at any one time, if I spend 1 minute teaching you, actually there are 7 billion minutes of work being done. Okay, at least. Okay, assuming nobody's sleeping. Okay, everybody is productive. Okay, so 1 minute talking to you, there are 7 billion minutes happening. Why? Because there are 7 billion people doing work in parallel. I'm talking to you for 1 minute, another person has cleaned the outside of my house for 1 minute, another person has designed a certain circuit for 1 minute, another person has just fueled up his petrol for 1 minute. So in 1 minute, 7 billion things are happening. Okay, so that's why we have advancements. Okay, because we are doing a lot of things in parallel. Next is get performance through pipelining, and this is what we're going to discuss in the next chapter. What is pipelining? Pipelining means break a process into smaller components. So I can just give you a small example here. So imagine this is the normal example I give you. This is McDonald's, and imagine we have a single counter in McDonald's, and the car comes in and goes out. So at this single counter, I'm going to perform 3 different operations. The first one is I'm going to order some food, and that's going to take 5 minutes. Number 2, I'm going to pay for the food. That's going to take 5 minutes. And number 3, I'm going to pick up the food, and that's going to take 5 minutes, a total of 15 minutes to go to a single counter of McDonald's. So I drive in, I wait 15 minutes, I do all my transaction here, and I get my Happy Meal. Happy Meal. Okay, so with fries. Okay, Happy Meal. And Coca-Cola. Okay, so happy. Okay, happy. Just put another burger there. Okay, right. Okay, so it takes you 15 minutes to complete, and if you look at this in 60 minutes, I can in 60 minutes I can serve 4 cars. Okay, that makes sense. Okay, I can serve 4 cars. So if every car takes 15 minutes, that is 5 minutes to order, 5 minutes to pay, and 5 minutes to pick up the food. In 60 minutes, I can serve 4 cars. Makes sense. So what I can do here is that I can do some pipelining, and this is what you see typically in many cases. So a typical pipeline will look something like this. Okay, so in the first counter, you order your food, and that's going to take 5 minutes. In the second counter, you are going to, you're going to pay for your food, pay $1, and that's going to take 5 minutes. In the third counter, you're going to pick up the food, and that's going to take 5 minutes. And assuming the delay between this is negligible. Okay, so we just want to make our case simple. Okay, so again, if a car comes in, it's going to take 15 minutes to get the food. Okay, to get the food. So that's pretty much the same. But what you can see here is that there's a little bit of interesting thing to see. Okay, so a single car number 1 is going to take 15 minutes to pass through the counter. Okay, 15 minutes to pass through the counter. So again, same, no change. So let me just break this down. The first 5 minutes, this is car number 1. The next 5 minutes, the car 1 here, and another car will appear at the back. In the 15th minute, the car is here, car number 2 is here, the third car is here. Okay, in 20 minutes, car number 2 here, car number 1 has finished, car number 3 here, car number 4 here. At 25 minutes, car number 3 here, car number 4 here, car number 5 here. At 30th minute, car number 4 here, car number 5 here, car number 6 here. At 35th minute, car number 5 is here, car number 6 is here, car number 7 is here. Okay, so just give you a quick understanding here. So this car number 1 took 15 minutes to buy. Same with this. It took 15 minutes to buy. Okay, same, no change. So this is the keyword. The latency is the same. In this case, the latency is the same, no change. What is latency? Here's a definition. Latency means the time, the moment you enter the process and the moment you exit the process. So the time it takes you to enter and exit the process is called latency. Another different definition, the time it takes from the moment you provide an input to the moment you start getting an output. Still the same, the moment you put an input and you start getting an output, that is called latency. Okay, that's called latency. So again, latency does not change, still 15 minutes. But here's a good thing. How many cars did I serve in 60 minutes with one counter? It's only 4. So one car comes in and sits there for 15 minutes and exits one car. So in 60 minutes, I serve 4 cars. But have a look here. With breaking the process into 3 smaller components, and that is what we call pipeline. Okay. Now what happens is that in only 35 minutes, actually in 30 minutes, in 25 minutes, okay, in only 25 minutes, okay, in only 30 minutes, I've actually served 4 cars. I've served 4 cars. So in 60 minutes, I will serve definitely more than 4 cars. I didn't draw all the way to 60 minutes, but you can see here, only half, until half already, you already serve 4 cars. So with pipelining, you have higher throughput. Okay, so this is another term, throughput. Throughput means how much work per unit time. So in this case, you only have 1 car per unit time. That is a 15-minute chunk of time. In this case, for every 1 unit of time, that is 5 minutes, we have 3 different works happening. Okay, at any one time, at any 5 minutes, 1 car is getting the food, another car is paying for the food, another car is ordering the food. So at any one time, there are 3 different things happening, but 3 work per unit time. Okay, so this has a higher throughput, which is good for McDonald's and car wash. If you've been to Malaysian car wash, for those who are not Malaysian, I think, I'm not sure in your country how it works. Okay, but if you're a Malaysian, you have a Malaysian car wash. Right? You go bring your car inside, they'll put a snow, then the next one they're going to spray water, then the next one they're going to vacuum the car, the next one they're going to dry the car with cloth. So it's a pipeline as well. Okay, so that's what it says, that we are going to get performance through pipelining. Okay, next is performance through prediction. Okay, performance through prediction. So just give you a simple case. Tell me what's going to be the weather tomorrow. And the weather tomorrow is really going to give you a big impact. For example, um, it is going to affect the choice of mode of transport for you tomorrow. For example, you go to Intel campus, which you don't, okay, but imagine you go to your office, you got two choices. You can either walk, since it's just 2 kilometers away, walk, or you can drive. You most likely want to walk because it's nearby and you don't have to go through traffic jam and so on. So you prefer walking, but it really depends on the weather. Okay, if tomorrow is going to rain, then you're definitely going to take a car. If tomorrow is going to be a sunny day, you're definitely going to walk. So your decision really depends on the forecast tomorrow. Okay, forecast. But how good is your prediction? How good is your prediction? If your prediction is 99.999% correct, then it's fantastic. You wake up tomorrow, you already have in your mind that I'm going to walk, so I'm going to wear short pants and some cooling clothes, and I'm going to walk. It's going to be hot, so I'm going to walk. So fantastic. You wake up tomorrow, you just wear and go out, and after walking for 500 meters, it's still hot, no problem. But what if your prediction is poor? Okay, poor. Okay. So what it means that you imagine that tomorrow is the forecast says it's going to be sunny, so you prepare yourself for sunny weather. No umbrella, no raincoat, short pants, shoes, and you start walking. After 1 kilometer walking, suddenly it started to rain heavily. That's going to be a big problem, right? So what I'm trying to say is that the only truth is at that moment. The only true weather is not the forecast. That's why the name is forecast. It's not guaranteed. The only true weather is at that particular moment tomorrow. Then only you know the truth. And if you know the truth at that particular moment, it's too late to make a decision. It's too late to make it. Imagine you at that tomorrow morning 9 a.m. you're walking. Now only you know it's going to rain. That's a bit late to make decision. Okay, so if only I can make a decision before, and if only I can make a correct decision before, then I can make a lot of, it will give a big impact tomorrow. So how is this so important? So this is so important because of this. In computers, you're going to have, or in life, you're going to have a decision making. So in computer, you're going to have something like, if a certain condition is met, okay, then you're going to do the following operations. If certain operation is not met, then you're going to do the following operation. So we have some true block and we have some false block. And that will actually look something like this in a flow chart. Is A greater than B? Yes, perform the true block. This is the true block. No, perform the false block by next step. And this is the next step. So there's always this decision making in our flowchart or in our program. So what does this mean? It means that in our code, if you remember our code, I give you a little bit of memory space just now. So we have some data memory here and we have some instruction memory or code. Okay, it's code. So this thing, the code, let me just draw this one. Sorry, let me just choose this. This thing, sorry, let me just fix that. This thing is here. While this thing, oops, sorry. Okay, while this thing is here. Okay, and this thing is here. Okay, so the problem here is that my CPU program counter, my CPU's program counter is showing here. After that, should it go here plus, let's say 4 memory addresses, or should it jump here plus 4, 8, should it plus 12? That is the question. So which one should I load first? Should I load the yellow or should I load this purple? Or in other words, if I have a pipeline, okay, and the decision is here, okay, so at the back here, Should I load purple or should I load yellow? That is the question. So which one should be loaded behind the pipeline? So that is the idea. So if I can properly predict that, most likely it's going to be a true condition. Most likely it's definitely going to be a true condition. So I can preload the pipeline in a correct way so that when it comes to that moment in time, it is already preloaded and I can just proceed smoothly. You can just imagine this like playing a game. Okay, I'm not sure how many games you play, how much games you play, but when I was young, I'm no longer young, that is, I used to play a lot of games. Okay, and if you play something like a first person shooter like Doom 3, Quake, what else? There's one very good one. That's from Valve. What's the game? Huh? Anybody knows that game? It's from Valve. Anyway, if you play those kind of games, so you have a certain level that you play on level 10, so you play, but on that level they have some secret doors and so on. So if you happen to find that secret door, which is very unlikely that you find, and when you enter the secret door, then suddenly you see the pop-up will be loading, please wait, loading that level. Okay, why? Because that is a part of the game that is very unlikely that people will find. So it is not currently cached or buffered in the memory. So if you enter that level suddenly, that will take some time to load. Why? Because it's not pre-cached. Okay, so just to give you a feeling like that. So if I can predict what's going to happen tomorrow, for sure I can preload or prepare for it. If I can tell you when it's going to be the end of the world, you can prepare early already. Okay, if I can tell you what's going to be the stock market for Intel tomorrow, you can straight away sell today if you know it's going to go down. Insider trading. Okay, so that's what it means. So performance through prediction. Okay, if you want to gain performance by at least, we are not saying we are going to be 100% correct, but at least if you can predict 80% or 70% of the time correct, then it's better than no prediction. Okay, next is hierarchy of memories. What does hierarchy of memory mean? Okay, hierarchy of memory means this. So we have our CPU here, okay, and the CPU talks to our memory, okay, RAM, okay, and the RAM talks to our hard drive. Could be solid state drive or something like that. And we have this register, which is a temporary storage in our CPU. And this is actually very fast. So if you're running at 1 gigahertz, so this is actually running at the same rate as our CPU. Okay, but our RAM is running significantly slower. So RAM is running in nanoseconds, and our regular hard drive is running in milliseconds. So even 1 millisecond is so small for a human, but the factor between nano and milli is, after nano is what? Microseconds. Huh? It's about 1,000,000 times slower, right? Is that correct? Or 1,000 times slower? If the data is not here and you have to go to hard drive, you can imagine how many times slower is RAM with hard drive. Of course, you say, doctor, one hard drive is running in millisecond, right? Milli is so small. I blink my eye is 1 second. 1 second is 1,000 milliseconds. 1,000, I don't feel it. 1 milli is nothing for me. You are wrong. If I request the drive for 1,000 requests, and each request is getting delayed by milliseconds. So imagine how much delay you are going to accumulate. And that is why if you have a slow hard disk drive rather than a solid state drive, you can see that you load things very slow. It's not the CPU that is slow. The CPU is fast, but CPU has the following problem. Okay, this is CPU and this is your IO data. The CPU requests data, and this is my clock. Clock. I request for data. I hope the data appears here. That is not true. Because this is so slow, the data appears here. So what do I do from here until here? What do I have to do? I do nothing. Okay, I cannot do anything. So the CPU runs idle from my request until the data appears. So there are thousands and millions of billions of clock cycles wasted waiting for IO data. Okay, so IO coming. This is simplified explanation, just to give you simplified explanation. Okay, just to give you the concept. Today's computer, of course, it doesn't do that. While requesting IO, it will insert some other instruction in between. We call that multi-threading. Okay, then we have coarse multi-threading and we have fine multi-threading, whereby when some IO is currently stalled, waiting for data, we try to run other execution on the CPU by switching in and out different things running on the system. That is more realistic, but for simplified explanation, I request something and then I have to wait. I wait, is my data not coming? So I waste a lot of idle time doing nothing. Okay, so how can I reduce such a slow process? How can I reduce this waste of time? So instead of talking to this slow big memory 1 terabyte, I introduce a faster RAM of just 16 gigabyte. And if this is still slow, I'll introduce an intermediate memory called cache. And if that is not fast enough, I'll have several layers of cache. Cache level 1, cache level 2, cache level 3 with different speed and size. Okay, and fastest but small, bigger but slower. So now I have small into big memory cache. So caching is to show to make big slow memory look fast. That's the thing you must remember. Caching is to make big slow memory look fast. That's the whole purpose. Okay, it's the same thing that you have in your YouTube. In a YouTube, YouTube, you buffer. Buffer is caching lah. When we have the bandwidth, we quickly download as much as possible and we buffer it so that when the network becomes slow, we have some backup in our memory, so we don't have to wait for the slow network. Probably in the future, maybe in the next 5 minutes it becomes slow. You never know. So we buffer first. So that's actually caching. The other one, I can probably give you another example of caching is, you have this toilet in your house, right? Toilet, and then this is a toilet, right? And then you have this flush, right? And you flush from here, right? Why you need this tank? Why don't I just connect this pipe direct to the main pipe? Because we want to buffer. We want to buffer the water there. And then when we request a burst, water burst, burst data transfer burst, then we have a buffer. We can burst very quickly at high data rate. In this case, water. We want a high flush water to flush away something. Okay, something. All right. So that's the reason. Okay. Just for the fun of it, can I find brown color? Yeah, we put some brown color there. Now you know what I want to flush away. Okay, so that's like caching. That's like caching. So another great idea is that having hierarchy. Hierarchy means big memory, smaller but faster, small memory cache, even smaller cache but even faster cache, even smaller cache on top of the memory. That's what we call a hierarchy with memory. Just for the fun of it, we can always open CPU Z. I hope I have it on my computer. Yes. What is this? WinRAR is the only program I never buy. Before I die, I must pay for WinRAR. Okay. Okay, let's just open this CPU ID to give CPU information about my computer. Do you want to upgrade? What is this? A new version is available. Okay, I'm going to continue. All right, so if you see here, of course, I have this big memory. That is a 32 gigabyte DDR4 running at 2 gigahertz clock rate with a dual channel. That's my RAM. Of course, I have some latency. You see there's some latency. Request for column access strobe and row access strobe on my memory. And this is the delay. So when I say I want a memory, I give you an address, it will take some time. I say this address will not get the data right away. It will take some clock cycle to select the row and column at the memory bank. Okay, so there's going to be some delay here. Why is it so slow? 1 gigahertz. It's not running at full rate. Never mind. No, it is full rate because my RAM is actually 2.4 gigahertz, 2400 megahertz. This is 1200 megahertz. You can see that 1.2, but this is a dual channel. Sorry, DDR, double data rate. So on every clock edge, so double of this will be 2.4. Never mind. So that's my RAM. And if you look under my CPU, you'll see I have level 1 data cache, level 1 instruction cache, level 2 cache, level 3 cache. So I have 3 levels of hierarchy. Okay, from 32 kilobyte cache all the way to 8 megabytes of cache. And if this is not sufficient, then it go to that 32 gigabyte RAM. 32 gigabyte RAM not sufficient, it goes to the hard drive. Okay, so this is what we call hierarchy. Okay, just to show you that it is practical. It's not It's not something that's not practical. Finally, dependability via redundancy. That is, we create things that we don't need in order to introduce redundancy. Why do we have 2 cars at home? You just need one. Why do you have, I don't know, a spare tire in your car? Why do you have a spare tire in your car? You just need 4 tires to drive your car. You don't need the 5th tire. So the 5th tire is to create redundancy. Redundant means not needed. Okay, why we need this not needed thing? Why do we need this not needed? Because we want to have dependability. Dependability means that if one fails, we have a backup. Why do we need to back up our data to an external drive? I thought internal is sufficient. No, if internal fails, we have the external backup. Why do we need 4 airplane engines? Okay, let's do a why do planes have 4 engines? Engine failures long time ago are relatively common, so providing redundancy with 4 engines was important for long range flights. So why we have 4 engines on the plane is to provide redundancy. 1 fail, we have 3. If 2 fails, we have 2. If 4 fails, we can still glide to the nearest airport. Okay, so on computers we also have RAID. So RAID is a storage where you, on your computer, we use a redundant, the name is redundant, array of inexpensive or independent disks. Okay, so we may have 5 or 10 drives splitting your data over. So if one drive fails, no problem, we can recover the data by regenerating the data from other drives. Okay, so why? Because we want to create redundancy. Okay, so that's the whole idea, the 8 great ideas. Okay. Okay, so let me just continue. Okay, so let's have a look at this abstraction again. I've mentioned this many times, so just a quick one here. It allows you to hide the complexity. Okay, we don't want to know the low-level details unless it is necessary. Okay, so for example, the ISA, what's ISA? Is the instruction set architecture. It's a promise and a contract between the CPU and you as a programmer. For example, you buy a CPU from Intel and I'm going to write a program for it. I'm going to write Microsoft Word for it. I'm going to write Photoshop for it. I'm going to be the developer who's going to write a program for your Intel CPU. Now, Intel, you can do whatever you want in the micro architecture. Go ahead, you want to make 7 pipelines, you want to make 15 pipelines, you want to put dual core, you want to put quad core, you want to increase the cache, you want to reduce the cache, you want to add new instructions, whatever, I don't care. As long as you promise me a certain contract. And that contract is the ISA. The ISA tells the programmer what are the available registers, what are the available instructions, and so on. So I will write my program based on this only. The underlying hardware, you can change. It's abstracted away from me. Okay. Sorry. Okay. The next one is the application binary interface. This is actually the communication between the software and the ISA. We call it the ABI. And finally, the implementation is the underlying details. That's all things that we can abstract away. We don't have to, don't know the low-level details. Okay. The simplest abstraction I can tell you is this. If you have written any code in any programming language, for example, C, then you will have a code to write the file called fprintf. So fprintf allows you to write data to a certain drive. Okay, or very simple. Okay, very simple. Okay, so let me just take this document and I just say save as, save a copy, and I can browse for certain folders. Okay, and I can browse to my desktop, I can browse to my C drive, I can browse to my Google Drive, I can browse to my OneDrive, I can browse to my pen drive, I can browse to anywhere and save. Right, you can do that. Now each of these different storage, they are running on different protocols. The internal drive is running on the PCI Express port. The USB is running on the USB pen drive is running on the USB port. The Google Drive is running on a network UDP TCP/IP protocol. Okay, so they are running on different protocols and ports, and they have different formats as well. My internal drive is formatted as NTFS. My flash drive is formatted as FAT32. My Google Drive is formatted as I do not know what. So for me, it is abstracted. All I care is saving to a particular folder. Now the operating system is going to do the underlying conversion. If it's written on NTFS, use an NTFS driver filter. If it's writing to a FAT32, use a FAT32 driver filter. If it's writing over USB, convert it into USB packets and send over the USB data, and so on. So that's what we call abstraction. You don't have to know the underlying details. You just say, I browse to the folder and save. Other than that, it's handled by the OS. All right. All right, so how does a CPU work? It's actually made using this. It's made using a wafer. Okay, so this is an example of a 300 millimeter wafer which contains 280 chips with a 32 nanometer technology. I think now Intel has what? Anyone can put on the chat. If I'm mistaken, I think I'm mistaken lah. I'm a little bit outdated. I put it in the chat. It's 10 nanometer plus plus plus. Is that the current technology node at Intel, or Intel already has 7 nanometer? Okay, I'm not sure. If you have the info, you can just write in the chat. Um, I have no idea. I think 10 nanometer plus 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 is the last node that I remember lah. Okay, after that I also don't follow all this technology advancement also lah. Okay, sometimes I follow, sometimes I don't. So I'm not quite sure. So I think it's, since you're working in Intel, probably you know. Okay. So we build our chip on this wafer, and then we cut the wafer lah. Okay, we cut the wafer before we package it. So the process is like this. What is the feature size? The nanometer, you know, the feature size, that actually tells you the minimum transistor size or wire in the X or Y dimension. In 1971 was 10 microns, down to 0.011 micron in 2017, and now it's just 10 nanometer transistor. Okay. Of course, I think TSMC, Texas Semiconductor Corporation, is 4 nanometer, and I think they'll be coming up with 3 or 2 nanometer by next year. So Intel is a bit behind on that. Okay, and you can see here the technology trend that we have. The top one is the graph for DRAM capacity. You can see recently RAM capacity has also increased rapidly, but now it's actually saturating a bit. A long time ago, in year 2000, we have 256 megabytes of memory. 10 years back, 1990 is 4 megabytes. So from 4 megabyte increase to 256 megabytes. From 2000 to 2010, in 10 years, we increased from 256 to 2 gigabyte. And of course, today even my laptop has 32 gigabytes of memory. So, technology allows us to improve both in RAM capacity, and also down there the table is on the what we call transistor technology, from vacuum tube all the way to ultra large scale IC, where you have billions of transistor per chip, and which means the cost is also cheap lah. Okay, relative performance and per cost is very good lah, very good performance per cost. Okay, so the trend also follow the following way lah. Every year, basically, transistor density increases 35% per year, die size 10 to 20% per year, and integration about 40 to 55% per year. DRAM capacity is increasing 20 to 40% per year, but slowing down. Flash capacity is 50 to 60% per year, and magnetic technology is also slowing down 40% per year. I think now it's a bit down lah. Okay. It's not much magnetic, this technology you can compress on the platter already. Okay, and how do we measure performance? So performance really depends on a metric. Okay, very important. If I want to ask how good you are, for example, okay, I want to know how good you are, there must be an objective way of how to measure your performance. So the simplest way is, of course, is looking at your grades lah. Whether you get an A. Just 1 second, I need to scold my children. Okay, it's a Saturday, so kids are at home. Okay, Sundays I work in the office because I'm from Johor Bahru. Johor Bahru working day is from Sundays to Thursdays. Okay, so Sunday to Thursday is a working day in Johor. So tomorrow I'll be in my office, so it'll be much quieter, much quieter ambience, okay, and also aircon in my office, and no aircon in my in this room in my house, okay, so a bit hotter here. Nevertheless, if I want to measure your performance, there must be a metric. Okay, so I hope you don't have the same problem at home, Alicia told. Okay, oh my God, I dropped a staple on my keyboard. Hopefully it doesn't go in between the keyboard. Just 1 second. Okay, safe. Okay, these are the kids lah. They play with the staples, okay, and then they, and then these are very dangerous. I can go in between my keyboard and destroy my motherboard or whatever. Okay. Nevertheless, if I want to measure your performance, there must be a metric. Metric means a measurement lah. I mean, I cannot measure your weight using a ruler. It doesn't make sense, right? So I cannot measure your performance without a proper metric. It could be grades. I want to see who got the most A's in class. That's good. One way of knowing who is the best. Or your CPA or your GPA. Those are some of the ways we can measure performance. Okay. So on our computing platform, what we want to see is response time. That's one, number one. How fast does a device respond to input? Okay, or your processor responds to your input to do the processing. That's one way. The other thing is how much work you can do per unit time, and that's called throughput. Okay, and when we have 2 or 3 different machines, one way of comparing is to use relative speed up. Okay, relative speed. We are not going to say that this is 2 gigahertz system and this is 2, because that's very difficult to say. You know what? Back then in 1990 or maybe early 2000, I don't quite remember. You have this Pentium 4 processor. The Pentium 4 processor at that time was 2.4 gigahertz, the clock rate. And today you can even buy an Intel Core i3, also 2.4 gigahertz, the base clock rate. Okay, same clock rate. So if you just do a direct comparison, a 2.4 gigahertz and a 2.4 gigahertz, okay, yes, name. Okay, a 2.4 gigahertz and a 2.4 gigahertz is not fair. It's not right. It's just a number. The gigahertz is just a number. There are a lot more details in it. So what we can do is we can do a relative speed up comparison. Do something common that you like to do. What you like to use some simulation software. Perform the same simulation on the Core i3 2022 and same simulation on the Pentium 4 year 2000. Okay, you'd like to do what? Photoshop. Take the same Photoshop application, take the same image picture, and you do Photoshop on the 2022 Core i3 and do the same thing on the year 2000 Pentium 4 running at the same 2.8 gigahertz, and you get the time of the execution. So then you do the relative speed up. The speed up on the old machine over the speed up on the new machine will tell you that the Core i3 of the 2022 is 4.9 times faster than a 10-year-old processor, for example. So that's another way of measuring performance. Now, if you look at execution time here, how do you measure execution time? So there are 2 ways of measuring execution time. The first one is how long does a CPU take to process the information? So we call that CPU time. Just consider the CPU. Forget about RAM, forget about IO, forget about memory access, just how much time the CPU takes. We call that CPU time. Okay. The other one is called the wall time. The wall time means that the total time. In other words, you have a clock and you put it on the wall. And it's time. The time is now 10 a.m. The time is 10 a.m. And then you start executing your work. Open the picture Photoshop, run the filter in Photoshop, save the thing back to the drive. The whole total time, how long? It now from 10 a.m. becomes 10:10 a.m. 10 minutes. So the wall time means everything in the complete process. Okay, so wall time means every computation, all system overheads included. We call that wall clock time. Okay. Of course, when you say do something common, we need to have a certain benchmark. Okay, so for you, how do I know you may be attending computer architecture in my section? Some other students are attending computer architecture in a different section. For example, of course, we only have 1 section this semester, but assume we have 2 sections. Actually, we do have 2 sections, okay? One is in a different place. So imagine you are attending with Dr. Osman, another person attending with Dr. Nazir, different people, same material. How can I make sure who is better? okay, is through a benchmark. A benchmark means a same common operation or test. So what I can do is I can give the same test or same final examination to you and also the other section. So you're attempting the same final examination, and if you get better than the other section means you are better. So benchmark means you run the same operation on different CPUs. We run the same matrix multiplication on two CPUs. We run the same 3D graphic generation on two separate CPUs and see who comes on top. So that's what we call benchmarking, and we can use that to measure performance. And again, I already mentioned to you about bandwidth and latency just now. Okay, bandwidth or throughput means how much work is done per unit time. And latency means the time between the start and the completion of time. So I'll just give you another example here before we take another 5 minutes break. Okay, at 10:35 is so that you get the feeling that the fundamental concepts like that. Okay, so imagine you have this highway, and this is the city of Penang, and this is the city of Kuala Lumpur, and the distance is 220 kilometers. I think I have no idea at all. I have never driven from Penang to KL, so I do not know. Maybe I have driven to UTP, Petronas, a long time ago. Great. So if I drive my car here at 110 kilometers per hour, then the latency is the moment I enter this place, the moment I enter Penang, enter Penang and exit to KL, is going to be 2 hours. Okay, 110, 220 divided by 110 is going to take 2 hours to travel through this highway. That's called latency. Okay, and if the latency, what it means is that at every 2 hours, one car will pass through. Every 2 hours, one car will pass through. Okay, after 2 hours, one car. Then after that, the next car, the next car, the next car. Okay, so that's going to be the latency. Now, how can we improve the latency? Now, we can improve the latency, that is reduce the latency, by driving faster. So if I drive the car at 220 kilometers per hour, then it's just going to take me 1 hour to travel through the highway. Okay, so if I can run my CPU at a higher clock rate, 1 gigahertz, now I make it 2 gigahertz, which means things will run 2 times faster. So the latency will become shorter. Now, how can I increase the throughput? Throughput means more cars pass through the highway. How can I make more cars pass through the highway? One way is drive faster. Tell everyone drive your car faster. This way, more cars can go through the highway in the same amount of time. Okay. Or the other way is the safer way. The safer way is to introduce 2 lanes or 3 lanes. So even though everyone is driving at 110 kilometers per hour, but having 3 lanes means that 3 cars can pass at any one time on the highway. So every 2 hours, 3 cars will come out from the highway. So this is like, how can I increase the throughput? By putting more CPUs on the system. 1 core, 2 cores, 4 cores, 16 cores, 64 cores. So adding more processors on the system will increase my throughput. Means I can do more work per unit time. Okay, so that's the difference between latency and throughput. Okay, so you might as well have a look here. Okay, I say 11:35, right? So when the time comes, we'll just have a break. So you can see here that what is this graph is trying to show? Give me 1 minute to think about it. Latency versus bandwidth. So this graph is showing you the improvement in both latency and bandwidth for different kinds of technology. Okay, if you see here, in terms of microprocessor, this is a microprocessor, the sort of bluish purple, bluish line there. This microprocessor, the relative latency improvement is almost straight line and bandwidth, but things like network, okay, things like network, the latency improvement is not much compared to the bandwidth. Okay, and for the memory, with the latency is not improving much. Okay, but the bandwidth is increasing a lot. That's why your memory, we have things like dual channel, dual data rate, that actually allows faster, what we call faster a faster data bandwidth, more bandwidth. You have dual channel memory, then you have double data rates, you have more bandwidth, but the latency is still the same. Okay, means the clock cycles to wait for the data to come, still the same. Okay, maybe a bit improvement, but not much improvement. So So just to give you a quick look, okay. So DDR4 CAS latency So the DDR4 column access strobe latency is at least 15 clock cycles. Okay, it's 9 or 10. Okay, never mind lah. You can see DDR3, the latency is 9 clock cycle, while DDR4, the latency has increased to 15 clock cycles. Okay, what about DDR5, which is new? Not many laptops. So DDR5 latency is 32. Okay, so DDR, the clock latency is 9. DDR3, 9 clock cycles. 4 becomes worse, 15. And DDR5 is now taking more clocks for the latency. Okay, so the latency in terms of clocks is not much improving, but this is half the story. Okay, why? Because at DDR5 the clock rate is also higher. The clock is also higher. You have more clocks to spend to wait, but the clock rate is also higher. But actually, if you calculate this, if I'm not mistaken, last time I did some calculation between DDR3 and DDR4, the improvement in terms of latency after including clock rate, of course, you can see this is 9 becoming worse to 15, but including the clock rate, this is running at 2.4 gigahertz. This is running at, I don't know, 333 megahertz. I don't quite remember. If you calculate again, then you'll realize that same. It's not much difference. Okay, not much difference in latency. So latency not much improving, but the bandwidth is improving. Okay, the bandwidth is improving. Bandwidth is still, I can still transfer a lot more data. Okay, so this is just a quick example, relative performance. So basically, very safe. For example, imagine I have a problem or a program. I have some Photoshop and I'm running on my 8th generation Intel CPU, and it takes 15 seconds to run on my 8th generation Intel CPU. Today, someone is trying to tell me, hey, why don't you buy a new laptop with the 12th generation Intel Core i5 chip? Okay, 12th generation. So I say, okay, fine, let me run the same program there. And when running the same program, it just took me 10 seconds. So the relative performance is the older program running at 15 seconds, the new program running at 10 seconds, and the new chip is about 1.5. So the new processor is 1.5 times faster than my older processor. Just a simple example showing a relative performance. Okay, again, this one I mentioned just now already, but it's written in a different way. Elapsed time means total time. Total time means wall clock time. It means that the time it takes, including processing, including I/O, including operating system, including idle time, including everything. We call it elapsed time, also known as wall clock time. This actually determines the system's performance, the whole system's performance. You know, I could have the fastest 12th generation computer, the latest 12th generation laptop. I have A. And I have B, which is my 8th generation laptop, the old one. Okay. And I run Photoshop. I take this Photoshop and run both on that. If I just consider the time it takes to run on the chip alone, on the CPU alone, how long does it take to run Photoshop on the 12th generation? How long does it take to run the Photoshop on the 8th generation? There's a 4th generation gap. Okay, just run Photoshop on these two chips. Look at the CPU only. How long does it take? The 12th generation is faster. Okay, so that is looking at CPU time. How much time you spend on the job. Do not discount, do not count I/O, do not count other things. Just look at the CPU. You will find that the 12th generation is faster. Great. But if I look at the overall system, my 8th generation has a PCI Express solid state drive with 32 gigabytes of memory and Windows 10. My new laptop has Windows 11, a normal SATA SSD, and just 16 gigabytes of memory. So there are a lot of different components at different operating system, different hard drive at different speed, and completing the whole timing. Oh, my old laptop is faster. Maybe. Okay, example. Why? Because I/O faster, that I/O slower. So when you add everything up, the new computer is slower. It's not the CPU, it's the whole computer. So that's called the elapsed time. So the elapsed time tells you everything is the system's performance. Okay. All right, so finally, before we take a break, let's not take this. This will take a bit longer time to explain. So why don't I just give you a break first? It's 11:38. I'll see you back at 11:45. Or 11:45. That's a 7 minutes break. This will need some deeper explanation. So see you in 7 minutes. All right, so what we can summarize here is that the performance really depends on a couple of different things. The first one is how many instructions you have in your program. So this comes back to your algorithm. Okay, so sometimes your program, I mean, if you remember, to solve a problem, you can have different solutions. Okay, so if your program is taking 100 instructions, if your program is taking 50 instructions, so a program which is shorter will definitely be faster. Okay, in essence. Okay, so the number of instruction in a program also is one of the key criteria that impacts what we call our performance. And so the number of our instructions in a program, okay, is one of the factors that's going to contribute to the performance of our program. That's the CPU time. The next thing is that how many clock cycles is used per instruction. Okay, so is every instruction going to consume one clock cycle? Some instructions are going to consume more clock cycles. Okay, so how many clock cycles are used per instructions on average? Okay, because on our CPU, not all instructions are going to have the same number of clock cycles required for it to complete. So normally we represent them in terms of average. Okay, so the lesser clock cycles required is better. Okay, the lesser instructions per program, better. The lesser clock cycles per program, better. Okay, and finally, how many seconds per clock cycle? Okay, which are in other words is the clock rate. Okay, it's actually the clock rate. Okay, so this one, the bigger the clock rate, the better, which means the higher gigahertz means better. So this, if you multiply all of these things, is actually going to give you the total CPU time. What I'm trying to say is that you could have a CPU that has a high clock cycles per instruction, okay, but it's running at a very high clock rate as well. Okay, versus another CPU which may have um, less clock cycles per instruction but has a lower clock rate. So in the sense, both CPUs are the same. Okay, so you just can't look at just one thing. You can't just look at the clock rate and think that is sufficient. You have to look at all these three parameters that contribute to the CPU time. So let's see what different aspects of our system, okay, basically affects all of these things. Number one, the algorithm. The choice of algorithm, whether it's an efficient algorithm, whether it's a good algorithm or not. Just 1 second, please. Okay, so the algorithm, okay, whether it's an efficient algorithm or not efficient algorithm, will determine the instruction count. Okay, sorry. IC means instruction count, not integrated circuit. So good algorithm will generate good instruction count. A poor algorithm will generate a lot of instructions. So algorithm will affect your instruction count and possibly will affect your cycles per instruction. The choice of your programming language will also affect your instruction count. A certain programming language will use a lot of instructions. Certain efficient programming languages will generate smaller instruction count. Okay, and also this will also affect your CPI. While compiler, how good the compiler can optimize the code will affect the instruction count and also the CPI. Okay, and finally, your CPU's instruction set architecture will determine what are the instruction count going to be generated, what is the average CPI, and what is the period of your clock cycle. Okay, your ISA, your chip itself will determine the clock rate, will determine the CPI, will determine the IC, because your chip will tell you what are the available instructions to be used. Okay, so these are the different components of our system and how they are going to affect your CPU time. Okay, so how can we benchmark our CPU? We have different kinds of CPU benchmark. You can see here, one of it is, for example, the spec CPU 2006. This one actually will measure the elapsed time. Okay, and it actually summarizes the mean, the geometric means of the performance ratio. Basically, it runs a couple of different programs in it. It says here a selection of programs, a sorting program, a zipping program, a zip a folder, sort some data, perform some filtering, do some Fourier transform. So it has a couple of different types of workload. Some are memory intensive, some are compute intensive, some are IO intensive. So you have different kinds of workload. You run it, you take the geometric mean, and that gives you a rating. Okay. I'm not sure if I have so this example, CINT 2006. So inside this CINT, we have a couple of different programs running. We have some string processing, sorting, C compilation, AI, quantum simulation, video compression, XML parsing, and so on. So it performs several different applications and gets some values and CPI and performs the geometric mean to give a ratio. So you can run the same benchmark on all different CPUs you have, and then you can see which CPU is better than the other. Okay, so just give you a feel for it. So let's say CPU benchmark. So this is a software that you can download to see to run the benchmark on your CPU. Of course, I'm not going to run this, but I'm just going to see the available CPU. So let me just search my CPU. Let me just click that. It's taking a bit time. And let's say 8550U. That's my CPU. I bought it 4 years ago, this laptop. So it seems based on the benchmark, it is below the 855Y. Okay, with a rating of the rating going this way. Higher is better. I think the rating is not sorted. Can I press this sort button? Okay. There you go. So my 8550U is faster than the Xeon E3. Okay. Slower than the AMD FX 8350. Okay, let's see what's the latest Core i5, latest 12th generation Core i5. Yeah, 12400T, I think it's for the desktop. These are all desktop chips. Never mind, we just pick one of it, 12400. And this one is, my rating is 5956. Let me just find this one. The rating is 19,000. Oh my God. So you can see how far the difference of my 4-year-old laptop and today's desktop processor. This is today's desktop processor. Let me just try to find Core i5 laptop processor. Laptop, they have a different model number. If anyone knows, you can just put it in the chat so I don't have to search. These are all desktop one. I think it's all desktop one. Maybe 11th generation. 12th gen. This is laptop 1155G7. So let's try to find this. 1155G7 has a rating of 10,000. This is Core i5, Core i5 10515. So that is the 11th generation. That's the 11th generation. Okay, and my 8550U has a rating of this. Okay, and this was purchased in 2018, 4 years ago. Okay, and based on this, this is an i7 laptop in 2018, and this is an i5 laptop in 2022. Okay, and the difference is this. So the relative difference based on this benchmark is 10,0515 divided by 5956, 1.7 times faster. So 1.76. So this is 1.76 times faster compared to my 4-year-old laptop. So if today I want to go buy a laptop and someone says, hey, you should buy an i5, and I say I'm using an i7, I say, oh, i5 is slower than i7. And not necessarily. Based on the benchmark, it seems that today's i5 laptop series is almost 1.7 times faster than my 4-year-old laptop. So going from i7 down to i5 will still give me almost double the performance improvement. So it's a good time for me to purchase a new laptop. Okay, I guess. So you can see that this is a benchmark. Okay, of course you can learn more about the CPU benchmark, and it will tell you what does it do. It performs a performance test and it will give you the details what it will do inside the performance test, the description. You need to read more details. So what is that? It performs some integer operation, it performs some compression, it performs some prime number test, it performs an encryption, floating point. It performs all of this and gives you one rating. That's all. That's all what it does. Okay, so this is another test, an older Tesla since 2006, and the Core i7-920. Core i7-920 is the first generation Intel CPU. Okay, first generation, 920. Let's see if you can find that. 920, just for the fun of it, whether it's on the benchmark list or not. 920. This is the Qualcomm one. No, not this one. That's fine. Celeron. Probably this one lah. This one. Intel Core i7-920. 2000. The rating was 2000. So compared to the i7 back in 2006, is it 2006? You can do a quick Google search here, and you will see the Intel archive. So this is Intel archive. It will tell you what year it was released. So this was released in 2009, quarter 3 2009, 2019, 2022. So it's already 13 years back. 13 years back. So the performance for a desktop processor 13 years back was 2000, and my laptop is 5000 plus. So my laptop is almost 2.5 times faster than a desktop CD i7 in 2009. Okay, of course my laptop is 2018. That is 9 years after this one. Okay, just to give you a rating. Okay, so there's another important thing is that the Amdahl's law. So the Amdahl's law, if you've heard of it before, tells you that the proportional improvement in your overall performance. So what it's trying to tell you is that, you know what, the improvement that you can give to a system really depends on the portion that you can improve. Okay, the portion that you can improve. So I can rewrite this in the following way. Okay, so imagine this is the whole process, 100%, 0 to 100, 100% process. This is IO, this is some memory, and this 60% here is actually compute. Okay, so if I can improve my CPU performance, it's just going to affect this one only without affecting this 40% here. Okay, so what it's trying to tell you here, if this takes 100 seconds, okay, and this is the benchmark 1x. If I can improve this by cutting this to half, 50% improvement, then what we'll have is this 40% IO, and this is cut down to 30%, half. So this will become 70 seconds. So the improvement is 100 over 70. Okay, that is, let me just launch calculator. 100 divided by 70, that will be 1.4 times faster. If I can further improve this to become 0, let's say the best case. So this 40% and this becomes almost 0. Okay, so approximately 40%, 40 seconds only. So the best improvement I can get is 100 over 40, which is just 2.5 times performance improvement. So Amdahl is saying that, you know, the maximum improvement you can get is actually limited. Okay, just because I have a system with dual core, and if I put 4 core, from 2 become 4, I'll get double the performance. From 4, I become 8, I got 4 times the performance. From 8, I put 16 processor, I get 8 times improvement. No, it doesn't work that way. Okay, it really depends on how much of the process that can be improved by adding the new aspect in the equation. So if the whole process includes IO, includes memory, includes processing, so improving the processing will only affect one portion of your total time. So in this case, even if I can improve the CPU using a 1 terahertz processor, you know, fictional processor and can cut down the time from 60 seconds down to almost 0 seconds. Still, your whole processing is limited by the IO and memory, so your total improvement is just 2.5 times faster. You're not going to get a million times faster. Okay. Okay. Another way or another metric to see the performance is called MIPS. Okay, and to be careful, MIPS is also a name of a processor. In this slide, MIPS means millions of instructions per second. So it tells you how many millions of instructions the CPU can perform in 1 second. Okay, but this has to be careful. Why? Because the different CPUs may have different number of instructions for the same problem. Imagine I want to perform fast Fourier transform, FFT. I want to perform FFT. So on CPU, Intel CPU, it will require me 100,000 instructions. On the ARM CPU, it will require me 80,000 instructions. On the RISC-V CPU, it requires me 95,000 instructions. So if I ask you which CPU can perform most instruction, you will say, oh, the Intel CPU can perform 100 million instructions per second. Fine. But for the same problem of FFT, actually the Intel CPU is slower. Although it can perform more instructions per second, but the generated code is also longer. Okay, so here it tries to tell you that millions of instructions per second is one aspect, but it's not a complete true story. Why? Because there are other factors as well. Okay, so let's look at another aspect, which is called power and energy. Besides performance, we also want to look at power consumption. Okay, power consumption is also important, especially when you have things which are running on battery. We want it to last longer. And of course, like my laptop right now, if I put my hands here, it's kind of hot. What it's trying to tell you is that when you have high performance, you consume more power. You have a higher TDP, which is thermal design power. And when you have higher TDP, means you need cooling now. Okay, cooling means that you need to have active cooling or passive cooling. Passive cooling means you have to put heatsink. When you put heatsink, the things become thicker and becomes heavier. So for some application, that is not good. If you have a heatsink in your laptop or in your phone, becomes thicker and heavier, and also it become costly. Adding an extra component means more cost. So that's one thing. That's passive cooling. Now, when you have active cooling, now you need to put a fan. Okay, of course, fan has a limited cooling capacity. That is, at certain temperature, fan will no longer be able to cool the device. Then you need to go for liquid cooling. Okay, liquid means you bring out the temperature, bring out the heat using liquid, just like your aircon and your inside your car. Inside your car, you've got coolant. You put coolant, and the coolant will go through your engine block and bring out the heat to your radiator. Same thing with your aircon. You have that compressed gas. Gas goes into your indoor unit, grabs the heat, goes to the outdoor unit. The fan will cool the gas, and the gas will go inside again. So you may have to have different strategies for that. So adding a fan means you need extra power to run the fan. Means the device become thicker, and also will make the device become less robust, because now you have a mechanical moving component in your device. So those are some of the problems. So how can we reduce this power consumption? Obviously by going to a different process node, reduce the clock rate, which also affects the performance, and also turn off components. So when you're not using your Wi-Fi, it will power down the Wi-Fi module. If you're not using a Bluetooth, it will power down your Bluetooth module. So those are another technique to shut down components which you do not use. And you can see here the Intel's 386 CPU only consumed 2 watts of power, and the Intel i7 all the way to 130 watts. And so over the year, the power consumption has a big change because of different nodes and also different strategy. Instead of running at higher clock rate, why don't we put more cores on the system? This way we can have higher throughput at a lower clock rate. So instead of making the CPU run faster, why don't we slow down the CPU, but we put more CPUs in the system? So that's another strategy to reduce power consumption. And of course, the power is determined by the following components. The first one is called the dynamic energy, which is when the CPU changes from, the transistor changes from 0 to 1 and 1 to 0 states. That's where you have the dynamic energy consumption. And the equation for that is half times capacitive load times voltage square. And the dynamic power is obviously half times capacitive load times voltage square times frequency. Okay. And if you look at this equation, how can you reduce this power consumption? One is to play around with the capacitive load. Unfortunately, once you have the fabricated processor ready, the capacitive load can no longer be changed. It's part of the process. Okay. So you have to work on the different transistor process to have different capacitive load. But things like voltage and frequency can be adjusted while the processor is running. So this is where you have dynamic voltage and frequency scaling. Okay, so let me just give you a quick feel of this. Don't worry, we'll finish by 12:30. Okay, I think we don't have we have under 11 slides remaining. Okay, so let's have a look here. Looking at my CPU here, you can see that the clock rate is adjusting depending on my workload. Something is 2.9 gigahertz, something will go down to 1.1, and something goes up to 3.3. So this is your frequency scaling depending on your workload. And of course, there's also this of course, there's also this voltage scaling as well, but it doesn't appear on the task manager. It's not shown. I mean, as a normal user, you don't need to know that. I mean, why we want to know, right? But because we are studying this thing, so we can have a quick look at this. And if you look here, you can see my KB Lake processor, this i7 here, has a maximum TDP or thermal design power of 15 watt, and you can see the core voltage is fluctuating, and also my frequency is fluctuating as well. So this is a frequency and a voltage scaling depending on my workload. When there's no workload, this will go down. When there's workload, it goes up and down. So this gives you a brief moment of power management. You may think that, oh, you're just adjusting every millisecond, and that doesn't give a lot of improvement. Actually, that's not true. Every millisecond, if you can do very fine voltage and frequency stepping, that can actually save you a lot of power consumption at the end of the total day. Okay, so that's where we have this one, voltage and frequency scaling. Okay, for other components of our computer, we have things like RAM can run in low power state, drive can power down, your LCD screen can dim and then turn off. Okay, and for your CPU cores, some of them can be turned off and some of them can be overclocked. And if you know this, I'm not sure. By the way, all of you are from Intel or from different company also? If you're from different country, why don't you just put it in the chat? I'm from different company. Okay. If you have heard of this Intel's turbo boost technology, Intel, anyone not from Intel? Okay, if you're not from Intel, I can say. Okay, so Intel has this turbo or Nor Ashikin from different company. If you don't mind, you can mention the name of your company. Okay, so for example, this turbo boost. What is this turbo boost? A lot of stories here. Anyway, let me just go to the picture. Probably there's some good picture here. Yeah, this is the picture. So the turbo boost basically tells that nice poster here. Okay, Nemani, if you can look at it here. What it means is that when there's a full workload, Willow Glen MSC. Okay. I don't know that company. Later I'll Google. Okay. So this is all workload. So the CPU will run at a capped clock rate, so it is cool. But if only one core is having a lot of workload while other core is not much work, so it can boost the clock rate for this core. So instead of running at, let's say, 2 gigahertz, it can just push all the way to 3 gigahertz for one single core, as long as it is below the maximum temperature allowed. So it can push the clock rate all the way up to speed up the serial or single core application here, okay, because other core are not busy and we are still within the temperature envelope, so we can push it all the way up. Okay, so these are some of the strategies on this CPU. So this is the older one, a turbo boost. Now they have turbo boost 2, turbo boost 3, which I've lost track of. Perhaps if you're interested, you just have a look at what is this latest technologies all about. Basically what it means is that I can push a single core all the way maximum speed if it allows. Basically what it means is the road is clear, go and drive as fast as possible. When the road is full, you drive carefully. So that's what it means. And the other one is called this is all dynamic lah. This is called the static power lah. Okay, so static power scales with number of transistors. So if you want to improve the static power, you do some power gating. Okay. Okay, of course, when it comes down to device, comes down to transistors, comes down to that low level, it's completely not my expertise. You can just attend other courses lah. I'm not sure, analog CMOS perhaps, VLSI, nano electronics. Those things are abstracted away from me. Okay, I'm abstracted. I do not know these very low level things. In fact, I never took a course in these low level things when I was doing my master's or PhD. So definitely not my area, but basically you have other strategies to handle these transistor things, right? All right, so if you look at this chart here, we're almost at the end of the class, just to give you this boost of happiness, okay? End of morning class, okay? Okay, end of morning class, okay? You can see that the clock rate actually did go up, okay? But the power consumption, we managed to, control it, okay? Power is managed to be controlled. Now, one of the reasons is because of the dynamic voltage and frequency scaling. Other than that is because better process control, better process. The other thing is that more cores with lower clock rate, that's another strategy of doing things, okay? So finally, power is actually really depends on capacitive load, voltage and frequency. This actually gives impact of the total power consumption, okay? Using a lower voltage will definitely help power consumption. Okay, besides performance, there's always a benchmark for power consumption. Okay, so if you go to YouTube, you can see the benchmark of, they have all kinds of funny benchmarks, right? This is more practical benchmarks lah. So let me just say YouTube, let's say laptop power consumption benchmark. Okay, so for example, so this is a comparison. So what we have is they have some benchmarks like this. Okay, so these are the two different companies. One is from the Intel i7, the other one is Ryzen 7. So they did okay, so they did some sort of a benchmark. This advertisement is trying to ask me to buy a new laptop. Maybe I should. Okay, so just trying to see which laptop lasts the longest. I think that's the experiment here. Is it? I'm not sure. Or this is the performance benchmark. Maybe battery, laptop, battery bench. Okay. Okay, so they can have something like this, long battery life benchmark. So what they do is that very simple benchmark. They, what is this? This is an advertisement. Okay, let's wait for the advertisement to skip. Oh, very long advertisement. No. This is the video itself is like that. Something like this. So what they do is that they on the both laptop together. Okay, of course, at the beginning they did the benchmark for performance. At the end, what it is battery life. So battery life means that you on your laptop, both of them, and then you run them and play the same video over and over again and see which battery will die first. Okay, so you're going to see which laptop is more efficient. So that's where they do a sort of a real world benchmark. Okay, to a typical use, you run browser, you run YouTube, and then you run non-stop and see which battery actually dies first. Okay, so that's kind of a benchmark. Okay, so another way is simply to run a power benchmark like this. This is actually SSJ ops, or server side Java operations per second. Okay, server-side Java operations per second. It's again another kind of a benchmark to see how much power it consumes. And of course, they have their own equation, like how many operations you have. You take the average and divide by how much power you consume, and you average of that. Average of 10 operations, average of 10 power consumption, divide, and you get an overall server-side Java operations per watt. Of course, what we want is more operations per watt, means efficient. More work per less power. Okay, that's what we want. Okay, so here's a benchmark for the Xeon X5650. Some important things you can see here is that that maybe is important to see here is that when the server has 0% load, it's still consuming base of 80 watts. Okay, base of 80 watts. And if the server is running at 256 watt maximum power consumption, it's when it's 100%, it's using the maximum power consumption. Okay, so what you can see is that if we increase the load by 10%, you actually increase the power consumption by 41 watts. Increase another 10%, you just increase 14 watts. Increase another 10%, you increase by 11 watts. Increase another 10%, you increase by 11 watts. Another 10%, you increase by 13 watts. And here is just 15 watts. So you see here, if your server is doing no work, you're wasting a lot of energy and power. Okay, that's the whole idea that you can see from the benchmark. So it shows that it's in this chart. It shows here that at 100% is using 258 watt. At 50% is using 170 watt. That's 66%. At 10% is using 121 watt. That's 47%. So 47% of the energy, power consumption is spent at 10%. So this is very inefficient to run the server at this particular point. Okay, so and it uses the most power at 100%. So if you want to operate optimally, you have to operate between this range. Okay, to run at more much better what we call power consumption. Now coming back to this one, this is just an example showing that I have a new CPU which has 75% capacitive load of the old CPU and 50% voltage and 15% frequency reduction. How much power consumption reduction overall of my new CPU compared to the old one? So just use the equation C times V square times F. This is the C old, and 85% of the C old, V old, 85%. Okay, 15% reduction in frequency, 85% of the old capacitance, and 85% of the old voltage. Divide by the old, and you will get that you have a 0.5 50% power reduction by just manipulating the voltage and frequency. Okay, all right, simple mathematics. Okay, just an understanding there. Okay, and almost at the end, just some graphs here showing you that the different performance for different processes. So you can see the performance keep on improving, but with a different strategy of going for multi-core. So this is a last single core. Then after that, we have this all these are multi-core CPUs. Okay. So at the end of the day, what is the current trend? The current trend is to use instruction level parallelism. Okay. Our single processor performance does not go beyond 2003. After that, not much improvement in single core. So we need to do things in parallel. So we can do data level parallelism. This is if you have heard of Intel's streaming SIMD instruction or Intel's AVX, that is to do data level parallelism. Or you can do thread level parallelism through hyper-threading and multiple cores on the CPU, or maybe request level parallelism such as on servers. Okay. All right. So of course, the future strategy is to use multi-core. And do we have multi-core in this class? We just introduced and not much analysis on multi-core, if I'm not mistaken. Okay, so on a multi-core system, we have multiple CPUs on the same chip. If you have multiple CPUs on the motherboard, we call it multiprocessor. Okay, of course, using multi-core is not straightforward. You have to change your programming. So now the programming is written in parallel way. a same program, C program, you run on a multiple CPUs, will just use one CPU. You have to change your program so that it utilizes all the CPUs you have. So you have to reprogram your program, make modifications so you use multiple cores. So very important. And if you're interested, you can see things like pthread, things like OpenMP. This will allow you to change your program into a parallel program. Okay. So there's a problem there. Of course, problem of multi-core is how to make sure it gives you best performance, how to have a load balancing. So when there's a workload, it is evenly distributed on all the processors. So you have to balance that. So you have to have load balancing. How to communicate between different CPUs. This CPU communicate to the other CPU, communicate to the cache, communicate to the RAM. So there's also a problem of communication and also synchronization. Okay, so these are some of the things that when you do multi-core programming needs to be taken into account. Okay, so this is just a conclusion. Microprocessor really solves a lot of problem, but it is still limited to some sort of laws such as Amdahl's law. You have hardware enhancements that improve performance. Of course, today you can see my 4-year-old laptop and today's i5 is almost twice as fast. Okay. To measure the performance, we have to do certain kinds of benchmarking. Okay. And of course, not all laws will last forever. Okay. Moore's law is, some people say it's dead, some people say it's not dead. And then disk capacity also not improving from year to year. Now it's already almost saturating. And the constant power density is also, the Dennard scaling is also coming to an end. Okay, it says here that 3 nanometer might be the limit for our transistor size, but I think they have a 1 nanometer in some universities. Okay, so let's have a quick look this before we end our class. First of all, is Moore's law dead? Is Moore's law dead? You can search that. Moore's law is dead. Now what? So there are some people say, the simple answer is no, Moore's law is not dead. Is Moore's law dead? Some people say yes, some people will say no. Some people say it's not dead. Okay, so if you look at Apple's M1 keeps the Moore's law alive. Is that true? How Apple's M1 Monster M1 Ultra chip keeps Moore's law alive. So you can read about this. So it's really Moore's law dead? I have no idea. I don't know. Some people say it's dead. What it means is that can we still pack double the transistor every 24 months? Some people say yes, some people say no. Well, I'm not entirely sure, but Apple's M1 Ultra is actually a combination of 2 big chips patched together. So technically, it doubles the number of transistors, right? So it's not dead. Okay, it's not dead. Okay. Other questions that you can probably see is that 1 nanometer transistor. I think we have this already. By smaller, faster, stronger 1 nanometer by TSMC. The world's smallest transistor is 1 nanometer long. In Berkeley National Laboratory has built a 1 nanometer transistor. TSMC and MIT research claims amazing 1 nanometer transistor. So is 3 nanometer the limit? I guess not. They are coming. The IBM unveils 2 nanometer. Okay, there you go. Okay, so Intel's transistor current node. Does Intel have 5 nanometer? This is in 2024. I do not know. Maybe you know better. You work in the company. You know what is the best Intel transistor size. I think currently it's 10 nanometer plus plus. Maybe 7 nanometer. I have no idea. I'm not sure. I'm not clear about the current Intel transistor size. Okay, I didn't follow much. Okay, so if you know, you just let me know in the afternoon. What is the size of Intel's current technology? Intel's 12th generation chip transistor size. It's fabricated using Intel's 7 process, which is referred to Intel's 10 nanometer enhanced super fin. So I think this is 10 nanometer plus plus plus. Okay, this is the still 10 nanometer size. Is Intel Alder Lake? Is it Alder Lake? Is Alder Lake 7 nanometer? Intel finally unleashed a sub 10 nanometer. No, oh, so still 10 nanometer. Okay, but is it compatible to 7 nanometer? I don't know. These are something that people who work in this area should know better. All right, that's all for this morning. See you back at 2 p.m. For the next module. Take care. Have a nice lunch to those who are having lunch. For those who are fasting, have a nice break. See you back at 2 p.m. Assalamualaikum and bye-bye. Join at the same link. Okay, right. Thank you very much. Bye-bye.